And this is because we require explosive combinations of rewrite rules to perform the optimizations. So if we look at the blocking goal on the left, we already have millions of e-nodes and e-classes in less than 10 iterations. And if we look at the parallel goal, we exhaust memory already in the 7th iteration. So that was the 60 gigabytes of memory. So to get maybe a better idea of what we mean by long rewrite sequences, prior work that was using rewriting strategies required tens of thousands of rewrite steps to perform these optimizations, except the baseline. This is not the shortest path, the shortest possible path you can get, but that's what we achieved with manual rewrite ordering. And to give an example of what we mean by explosive combinations of rewrite rules, these are two example rules that quickly generate many possibilities in the eGraph. So here we have the split join rule, which if you look at the for loops on the right, it's about taking a for loop that is executed n times and splitting it into a for loop that is executed n divided by n times and another for loop that is executed n times inside. And that corresponds on the left side to a rewrite into the functional Bryce language. And the other rule is the transpose around map rule, which is basically about swapping nested loops. So instead of for n, we have for n. For the split join rule, we have split and join patterns on the functional side that enable this, and for the loop reordering, we have the transposition pattern that enable this. And you can quickly imagine that if you try to explore all possible ways to apply these rewrite rules, you get a lot of possible combinations. And to overcome these difficulties, we came up with sketch-guided equality saturation. So we made the observation that the shape of the optimized program is often used to explain the optimizations that are performed. On the left side, you can see how the loop nests are evolving if you want to apply the blocking optimization. So on the left, you have 3 nested loops, and on the right, you have 6 loops, such that in the inner side loops, we have this 4 times 32 times 32 block that is iterated upon. And it's not just something that we use in our work. We can also find something similar in the TVM paper, for example, so the compiler for machine learning, where on top of showing scheduling instructions that are specific to this compiler, they also show how the program shape is evolving during optimization. So the insight that we had is that these explanatory shapes can be formalized as sketches and used to guide the rewriting process. And this is a diagram representing how sketch-guided equality saturation works. Basically, the idea is to factor an unfeasible search into a sequence of feasible ones. So by first breaking these long rewrite sequences that we saw, and also by isolating explosive combinations of rewrite rules. So the idea is that the programmer provides a sequence of sketches at the top. We have sketches that we call sketch guides because they are intermediate goals to find. And then we have a final sketch which we call the sketch goal because that's the final the shape of the final program that we want to achieve. To satisfy each of these sketches, we run a search based on equality saturation. And that's why we can also specify different cost models and different sets of rules for each search. So if you think about the big step that is required to go from the term 0 to the term n+1 on the right. Providing this sketch guide is what is dividing the problem into smaller problems. And how do we isolate explosive combinations of rewrite rules? Well, because we enable different rewrite rules to be provided for each search, you may be able to only use the split rule in one search and only use the reordering rule in another search. So you avoid complicated interactions between them. So each search is based on equality saturation, but it's also slightly modified. So you can see what the changes that we made to equality saturations in red. Basically, on top of minimizing a cost function during extraction, we also want to satisfy a sketch. And in this case, what we've done is that we terminate the search as soon as a program satisfying the sketch is found. So there is no guarantee that we found the best program possible with the set of rewrite rules, but at least we found one program that satisfied the sketch. So what are sketches? Sketches are program patterns that leave details unspecified. So for example, this is the sketch for the baseline goal. And you can see that it specifies how the program should look like with a nesting of map and reduce patterns. So this contains map, contains reduce, and also it contains admiral is specifying what should be inside of the nesting. And again, that corresponds to an intuition if you think about for loops. So here we're just saying that we want to have a for loop that is executed n times, and inside a for loop that is executed n times, then k times. And we also expect to find addition and multiplication inside of the loop list. And these contains map abstractions are not built in, they are defined in terms of smaller building blocks. So here you can see that the contains add null sketch is in fact defined by using a building block called contains, and also a program call, which is the blue question mark. So the blue question mark basically is satisfied by any program. And we also have application nodes that are just regular nodes from the Rise language. And we say that the sketch S is satisfied by a set of terms R of S. So you can see on the bottom of this slide a formula that represents the set of terms represented by contains add null, and it's defined with a recursive formula. So if I just explain maybe the first line, the set of terms represented by contains add null is the set of terms that is represented by the application with the plus and the program role, as well as all of the terms that can be built from this. So we have the add null, the sketch for add null, that is kind of the starting point of this set of terms. And then we say that everything that you can build from the starting point is also a term satisfied by contains add null. And then there is something similar happening if you break it down into the smaller building blocks. And we can also define a sketch for the blocking optimization goal. Sorry, the slide is cut a little bit, but basically this is the same loop nest intuition that I showed a couple of slides ago. And the interesting thing is that if we want to rewrite a baseline program into a blocking program, we can provide a sketch guide which specifies how to split the loops before reordering them. So here you can see that on the right side with the for loops, we only split the for n loops into this for n divided by 32 and for 32 loops. And because of this, we are able to go from the baseline to the sketch guide by only running a search that tries to split loops. And then to do the next step, going from the sketch guide to the blocking sketch, we only need to figure out how to reorder loops. So it's much easier than trying to perform blocking in a single step. And we've evaluated sketch-guided equality saturation on this matrix multiplication case study. And at the top, this is the previous table that I showed you, where 5 of the optimization goals could not be found. And at the bottom, this is the result with sketch-guided equality saturation. So there is also an additional column that is specifying how many sketch guides have to be provided. So here we've provided up to 3 sketch guides for the most complex optimizations. And the first thing that we can see is that with sketch-guided equality saturation, we are able to find all of the 7 optimization goals. And we can also see that for the blocking optimization goal, which was previously found, we are able to reduce the runtime of the search by 600 times and to reduce the RAM usage by about 100 times. So we're getting a significantly easier search by providing this sketch guide. We can also look at how this impacts the eGraph evolution. So at the top, we have again the guided eGraph evolution, so without sketch guidance, where we're running out of memory for the parallel goal on the right. And at the bottom, we have the same eGraph evolution, but with sketch-guided equality saturation. And we can clearly see where the sketch guides kick in, so they are the purple vertical lines. And we can see that maybe the first thing to notice is that the scale on the y-axis has 3 orders of magnitude difference. So instead of having millions of e-nodes, for example, we only have thousands of e-nodes. We can also notice that even though for most of the searches we still have exponential growth, there is this one search at the end of the parallel goal that is only linear in growth. And that's because all the rewrite rules that have an explosive behavior were used for the previous sketch guides, and they were not necessary for the final search. We also looked at how sketches compare to the full programs. So these are the sketch guides and sketch goals that are required for each optimization goal, along with their sizes in terms of how many nodes they contain and the program size. So what is the size of the final optimized program? One thing that we can notice is that each sketch corresponds to a logical transformation step. So we have sketches for splitting loops, we have sketches for reordering loops, and we have sketches for storing values into memory. We can also see that sketches elide around 90% of the program. And you can't see it on the table, but I can also tell you that the sketches don't need to specify intricate details, such as the split, join, and transpose pattern that are kind of reshaping arrays. We don't need to specify this in the sketches. In terms of future work, we have a lot of ideas, but maybe the 2 things that I want to highlight is that we are interested in combining the automation of equality saturation with the precise control of rewriting strategies. So here we've done with sketch-guided equality saturation, we've achieved a middle ground in a way, but we're still not able to combine rewriting strategies with equality saturation, and would be interested in exploring this in the future. So for example, can we use equality saturation as a rewriting strategy? And I've seen that there is another talk today at 11:30 about equality saturation as a tactic for proof assistance. And I think that's a very similar idea. And then the other direction, which is, I think, much harder to think about is, can we use rewriting strategies or proof tactics inside of equality saturation? So yeah, I apologize if you don't know what rewriting strategies are. But yes, and the other future work that I want to highlight is that we're interested in in using sketch-guided equality saturation for more diverse applications. And I want to highlight this because I would like to know if you have a use case where you think sketch guiding would be a good technique. And in particular, I was thinking that it could be an interesting technique for theory proving. Yeah, and I will skip the other future work. So that was my talk. Thank you for listening. To conclude, we proposed sketches to guide rewriting, sketch-guided equality saturation, a novel semi-automated optimization technique. And if you're interested, we have a paper on arXiv where you can see all the details.
Thanks for the great talk, Thomas. I have many questions. I think this is awesome work, obviously, because I obviously this tough. But I would love to see if the audience has any questions. If they do, yeah, please. And then would you mind repeating the question because you have the text back?
So from the sketch guiding, it feels like that are you slightly constrained today? Can you discover novel, different designs using this sketch pattern because you're kind of leading it or helping its handle it? So either then discover new, unknown designs that you have come up with this week.
So is the question, how can we use sketch-guided equality saturation to discover unknown optimizations?
Unknown optimizations or combinations of existing optimizations that maybe haven't been done before.
So at least in this work, the focus was very much to provide this as a tool for the programmer, so the person that wants to optimize their program. And we're not really trying to discover new optimizations completely in a fully automated way, but how this helps the programmer is that they can explore different ways to optimize the program by writing sketches. So that gives them a tool to kind of tweak things and try different approaches. That also gives them the guarantee that whatever program is found will have the same semantics as an optimized program. So I think it's an interesting question to think about how this could be used to find unknown optimizations, but currently it's very much, I would say, a tool for the programmer, and it's not meant as a fully automatic technique. And maybe what would help in this direction would be to build an optimization assistant around this technique, so that where instead of providing a sequence of sketches, the programmer could have a more intuitive interface, maybe to play around with optimizations.
I was wondering, what is are sketches the same thing as the left-hand side of matching rules? Are they implemented as like, you pattern match on the left-hand side of the rule, like make a rewrite happen, but instead, are you pattern matching and then terminating and then extracting? Is that basically what it is, or is there something more sketches have?
So the question is, are sketches similar to the left-hand side of pattern matching rules? Mm-hmm. I think in general, I would say yes, but so for example, if you look at this sketch have a contains construct, which you wouldn't usually find on the left-hand side of the rewrite rule. I mean, I guess you could imagine a rewrite system that allows this, but I would say that compared to the standard expressivity of the left-hand side of the rewrite rule, we want sketches to have more expressive power. But otherwise, you can either see sketches as representing a family of terms, or you can see sketches as a pattern that can be matched or not. Yeah.
So what if there is no program that matches a sketch? In which case, aren't you going to go to the same million keyboard situation? And how do you tackle that? I mean, in terms of good user experience.
Right. So currently, what we would do is just set a.
Repeat the question.
Oh yeah. Yes. So what do we do if the sketch cannot be found and the search becomes invisible? So currently, what we would do is that we would just set a lower timeout, so lower constraints on the search to tell you, well, after many minutes of search and that much RAM usage, I was not able to find your goal. So yeah, if the sketch guide is hard to find, you still have the similar problem as before. But yeah, it's not a magical tool.
Alrighty, let's thank the speaker one more time. Alright, for our next talk in the opening session, Ian, you want to go ahead and start getting set up. We have Ian Briggs, and this opening session, especially because both of the speakers have full research papers associated with their talks, so I encourage you to go check those out. The remainder have abstracts, and you should definitely check out their work as well. But if you're looking to really dive in, these two have full papers associated, and those are posted on the program. So make sure to check those out.
Just need what? Should we just hold it?
Stay. How about you?
You have to pick a window.
Oh. Thank you. Sorry I used computer when I was small. Okay. Does that look good on Gavin? Cool. Well, hello, I'm Ian Briggs, and I'll be presenting to you today how to synthesize mathematical identities with graphs. I know it sounds amazingly interesting, but I'll be doing it using only 4 eggs. So what do I do in my spare time? I like taking math and turning it into code. So this can range from library implementations to fun little compound expressions. But when you do that, you have a lot of choices. Like, you want to use a table or a polynomial. What size table should you use? What polynomial degree should you use? What precision do you want it? You might even want to do mixed precision. Use a Taylor form for your approximation, or Remez, or I've heard Pade approximations. They might be useful. There's a lot of different choices you can make. I don't want to make all these choices manually. I just want to have something that I can say, here's some math, spit out to me a whole bunch of implementations that I can play with. Well, the first step of that is we need to do something called range reduction, and we need to automate that. So range reduction is when you're trying to implement a function, and like, yeah, I can match cubic polynomial to part of this, but I can't do the whole range. But the astute among you may have realized there's kind of a repeating pattern. All I really need to do is implement that, and the rest is just repeats. In fact, I don't even need to just implement that. I can go a little bit closer, realize that the left side is kind of rotated from the right side. Oh, look, there's one more step. You can go and just implement this red little line, and through flips, rotates, and repeat, get the entire math function, which is cool. I mean, these are all based on identities, like the sine of x is equivalent to the negative sine of negative x, or sine of x is equal to sine of x plus 2 pi. I want to find these automatic. Well, so going back to the dream of having a completely automatic math generation. First, you start with a math function. You find these useful identities. Use them to create some sort of code that uses them. Once you have this nice little interval where you can implement your function, you use your tables, or there's actually wonderful automated tools out there. Solia can do polynomials. If you've heard of RLibM, it is pure magic and can implement correctly rounded math functions. And then from there, you generate your code. Yay! As I said, I want to automate this, and but that's where you grab stuff. So I have these axioms. You can go grab a math textbook and say, okay, here's what sine does, here's what x does. And what I want is to have these compound functions and magically just pull out nice big identities. Now, we're going to want these to have the form of where you say, there it is. You take x, you somehow transform it with t, so that would be like you're dividing, you're modding, or there's other ways of doing it. Run that through your function, and then sometimes you have to do mapping, that's you're flipping and rotating. So we want things in this form, which, by the way, come on, I think I might have to steal your work, because right now we'll see what I do now, but it's a lot less complicated. So we can talk after. But the general kind of intuition here is that we can use e-graphs to take these individual axioms and build bigger identities. And we do this in 2 phases. First we generate, then we kind of slim down because of how the generation is done. So to generate, we take our function, our axioms, plug them into our first egg, and get out our identities. With the way e-graphs normally work, you get you have some hurdles we have to jump over. The first is they give us a best answer. When we extract, we get the best thing, which doesn't help us here. So what we did was we invented node extraction, where instead of taking an e-class and asking it, hey, what's the best representative for you? We rip open the e-class and say, hey, all you e-nodes, what best representative for each of you? So then we can get much more functions out, or expressions, sorry. So we can get things that are equivalent, but different. So now we have kind of the pool to start. But as I said, I wanted this shape of something done to the variable, fed through a function, then pulled out. And not even all these here match that. Well, I don't want to try to implement pattern matching inside the e-graph. So instead, I make a new operator, and I define it as my function and add that in. So rewrite whatever the body of my function is to f of x. Then during extraction, just give the low cost, so it's preferentially chosen. Now, wherever the pattern f appears, for f appears, it gets subtracted. So you can see like this is minus f of minus x. This one, there is no matching. So we would extract that and then throw it away. But now we at least have pulled out these functions in the shape we want. Okay, we need to thin these out, because at this point, usually per expression that I've put in, we have dozens, if not hundreds, of expressions, and a lot of them are useful. The first form that's not really useful is we get equivalent identities, 1 times something, or plus 0, or like divided by 2 plus itself divided by 2 again. Like, that's interesting, but they're all representing the same idea. So we need to get rid of those and pull out one representative example. We also have definitional identities. So you see here we have the covariance sign 1 minus sin of x. We have it multiplied by 2 and then minus f of x. This is just trying to embed the definition of our function inside the loop. It's not quite useful for our instructions. Finally, we have these kind of compound identities, where it's just 2 identities applied together. And so, like, I really don't need all of them. I just need representative examples that can cover the same space. So let's go back to these equivalent identities. This is where my second egg comes in. What we do is, with this fresh egg, we take our expressions without implying that they're equal and shove them into the egg. We put our axioms in and we don't tell it what f of x means. So now what we get out is things that are equivalent. So you can see here f of x is equivalent to f of x plus 0. And egg will tell us that. And we can just pick one from each representative group. This thins down by quite an amazing amount. But there's still more. We still have those definitional identities, which are the peskiest ones to get rid of. And if you have any ideas, come up. So the intuition here is, if I can take the identity and just show somebody, give them enough time, they can tell me what the original function is, it's way too specific. So our way of getting rid of this, we take f of x minus our identity, put that into our e-graph with our axioms, and union it with 0. Run for a little while, and then ask the e-graph, hey, is f of x minus our body in the e-graph, and is it equal to 0? If so, we had enough information to start with to define f of x, and we don't need this identity. Finally, we have these compound identities. So if you're looking at, let's say we've gotten down to these identities. Trivial identity, f of x, negative f, negative x, and then these 2 periodic identities. Well, we can take and cross them with each other. So like, for identity 0 cross identity 0, trivially we get f of x out. But if you cross identity 1 with itself, you get negative f, or negative negative f of negative negative x. That looks suspiciously like f of x. So we might, looking at this, we might actually not need identity 0, use identity 1 to generate. And that's kind of the intuition that we're going with. So we take and fill out this grid of our identities. We take and put them into our final egg and pull out these identities. Now, as I said, identity 0 can be achieved by crossing identity 1 with itself. Similarly, identity 2 can be used crossed with itself to create identity 3. What we want is a minimum number of these core identities that can be used to represent all groups. In this case, identity 1 and identity 2 are enough to cover all 4 of our identities. We've cut our problem in half. How we do this is we phrase this as an ILP problem and shell out Z3. So combining all these things, what do we do? Well, we have 61 input expressions that we have played with, and that first egg generates 7,215 identities. I am not reading those mine. So first, we get about 3,000 that don't even have that function in the expression, that don't match our form that we want. 4,000 about are removed by that second egg. So these are the triple identities. And it's a side effect of using this node abstraction that we get this, but you know, that's kind of the name of the game. Only 4 are removed by that incredibly clever way of removing definitional identities. This is where I need the most improvement. And then finally, 102 are removed by that cross product. After that, 19 are just f of x equals f of x because there's nothing able to replace them. So we have 106 identities that come out the end of the pipeline, starting from our 7,000. Looking at those manually, about half of them would be useful for implementing the math function, and half are additional versions of these definitional identities. So that's what we were able to achieve using just 4 eggs. Now, if there are no questions, I'm going to leave this slide here for people to go, I know. Like this first one, okay, you can move f of x over this side, and then I can get, okay, sine of x over 2. Now, okay. So, any questions? We can go with that. If not, you can stare at these and have fun.
Any questions for Ian? Make sure to repeat the question.
I'm sure.
Ian, awesome talk, thank you. As somebody who's not a math person, can you give me, your setup is really good. Can you give me intuition for how much it helps you define additional identities when you are trying to approximate functions? So you showed, how you can break apart sine into this tiny, tiny part, and you have to find those identities. Can you give me an intuition for how much each new identity helps you? Does it make the difference between being able to implement or approximate something and not being able to approximate it?
So the question was, how much does each additional identity help in actually implementing the mathematical expression? So if you're starting with just the number line negative infinity, you can't implement that with a polynomial or a table. And so those first couple identities take you from unable to implement to possibly implement. But the smaller input interval you have, the faster and more accurate you can be. If you're using a polynomial and you go from an input range of 0 to pi over 2 or to pi for sine, and you're able to cut that in half, you can shave off a couple elements in your polynomial and get the same accuracy. So these kind of reductions are very useful, and the hope is with this we'll be able to find some sort of maximal set of functions, but we haven't gone that far. Yep.
So I guess one way of looking at this would be saying you're finding symmetries of these functions.
Yes.
Are there any other applications you consider of that?
So the question was, what we're finding is basically symmetries of the functions. Are there any other properties that we find this to be useful? So far, none that we've really found useful. It has spit out some interesting answers, like f of x is equivalent to abs of f of x. Somehow the system was able to intuit that the function is always positive. We haven't found a use for that, but that is the kind of thing that would be interesting to find. So no, but I'm hoping.
So, 2 questions. First, have you only tried polynomial class of functions or other things also?
Sorry, I kind of walked quickly through that. So our input expressions are things that have sine, cosine, x, log, and in implementing things, you eventually get down to this small interval. And what we're doing with this work is getting down to that small interval. As far as the actual implementations, that's other tools that are already established.
So like you are finding polynomial approximation for that small interval. I mean, not like rewrite rule.
No. The rewrite rules aren't doing anything of that sort.
Okay.
We're only finding these identities that we use for.
Also, the second question is, I see that it's all equality right now, but can you like do somehow proof by contradiction? Like, you know, if something is less than like some boundary and it's more than such a boundary, then it's definitely equal. So maybe that's how you can get rid of those definitional equalities.
Yeah. We're gonna have to talk.
Yeah.
All right, let's take a one more time. And that's for the opening session. We're back at 10:30. I think.
I do have one last plug, which is on Thursday. If you want to see me fumble around more, I have another presentation I'm going to give.
All right.
Thank you.
So, this is a eGraphs workshop and a Datalog workshop, so I'll give a hot 1 minute introduction to Datalog. So Datalog is a bottom-up relative prologue, and what I find fascinating about it is that it's efficiently executable, but also has absolutely beautiful semantics. You can put on different hats to look at the same thing. You can put on your database hat to look at data model programs. You can think about it in terms semantically, in terms of expanding relations. And you can also think about it in terms of logic or inference rules. The Datalog clauses take the form of form clauses. And here's the introductory Datalog program that people always use to talk about Datalog. It's a connectivity and a graph. So it's 3 parts: facts, rules, and a query. The facts initialize a database with edges in the database. And so there's an edge table, and this is inserting a row AD, a row BC, and a row CD into an edge table. So that initializes the database, and then the rules apply to the database, where the right-hand side of the rules are queries, the analog of SQL queries, and then the left-hand side of the rule inserts those instantiated variables into the database, into those rows. So this first thing is saying that for every edge between x and y, there's a path between x and y, and the second one is saying if there's an edge between x and y and a path between y and z, there's also a path between x and z. And so the loop is, it queries the right-hand side, maybe it does some database joins or something. For example, this edge xy and path yz share over y, there's a join there. And then it inserts the left-hand sides, and it does it again and again and again until it reaches termination, which is another fantastic property, theory of Datalog, that under the appropriate assumptions, Datalog programs are guaranteed to terminate, even though they have this recursive form. And my Datalog also has a notion of query, for which it runs exactly the same thing as the right-hand sides of these rules, but it prints it out instead of inserting it back into the database. So if I click run, we see here that it actually does compute the transitive closure of edge, and you'll see that every vertex is equal to each other vertex appears in this table. Okay, so that's Datalog. But what is this actually? This is actually egglog 0, prototype implementation built on top of egg. This is compilable to the web because it's egg is built with Rust, and so this nice little demo. Heavily inspired by the relational e-matching work. Sort of the ideas here, and the idea is, what is a database? A database is in the eye of the beholder. Anything that stores data is a database. It doesn't have to be just tables, flat tables with simple objects in them. So eGraphs are a database, and what does this database hold? It holds terms and an equality relation between those terms, and maybe even an infinite number of terms. So egglog 0, as a subset of it, supports ordinary Datalog with terms. That's like the ordinary subset of it that you'll find in other Datalogs. And the rules operate very similarly to how I described Datalog rules previously. It queries the right-hand side of the rules, which is implemented using U-matching multi-patterns from egg, and then it instantiates and inserts the left-hand sides into the eGraph. So you can see this is very, very related to the e-matching process, the rewriting process. But what makes egglog 0 very special is the special equality, which is backed by eGraph equality / the union bind, under the hood. And when it appears on the right-hand sides of rules, it is the queries are only succeeding for which those two things are found to be in the same E-class. And when it appears on the left-hand side of the rule, it's actually asserting those things are in the same E-class. So it's calling union on the underlying union bind on the left-hand side of the rules. And finally, queries do e-matching. It's like the identical e-matching process as in the rules, but then it extracts every result it has to it uses the small term extraction to just print it out for the user. And here we have in the logical syntax, some familiar rewrite rules. If you add x to 0 and it's in E class E, then x is also in E class E. That's how you do that. And then if add xy is equal to is in E class E, add yx is equal in E class E. And that's commutativity. But there's also syntax sugar because rewrite rules are so common. Other things I'm going to talk about. That's Taylor 0 syntax sugar for the rewrite rule case. But it expands this. And so there's an overloading between predicates and terms in egglog 0. So if you want to initialize an eGraph with something you want to start chewing on,
you initialize it by stating it as a fact. So that's, operationally, that just inserts that term into the database, into the graph. So I initialize it with this, and then I want to extract a small term that is in the same class as this term. And if I run it, we have that A is in fact in the same class as F0A, because these rules got a little prepared. And so data log, you can have multiple pieces of the right-hand side of the rule in the body of the rule. And so that requires multi-patterns. Multi-patterns are slightly different from guards, kind of related, but guards can check, but multi-patterns can bind. They can bind new variables, where guards really couldn't. And for those of you, I know many in the room actually are implementing their own version of A and things. It's actually not so hard to implement multi-patterns if you already have e-matching. Essentially how it works, or one way you can make it work, is the e-matching compiler environment has a mapping from variable names to runtime locations, indices, and some runtime vector. And you just need to thread that between the separate calls to the e-matching compiler is basically how it works. This has actually been upstream to egg in the latest release of egg. It's already available, and you can try out the things that I'm doing here in raw egg and not using my surface syntax. Raw egg. Examples. Why do we care about this? What is interesting about adding this random extension to egg and changing from the rewriting paradigm to a data log paradigm? Well, there's a number of things you can express that just don't fit into the rewriting box. And what many of them end up being is finding an equality in the database and then asserting a new equality in the database. And rewriting is a subset of that, as I showed earlier, but these things really just don't take the shape of rewriting what's proper. So first one, common one, a familiar one, is injectivity. If you have two functions where the outputs are equal, it implies the inputs are equal if that function is injective. And examples of that are constructors is a very common one, but also addition, for example, when one argument is injective. And so here you can see this rule is saying that if two lists are equal, then their heads have to be equal and their tails have to be equal, is basically what that's saying. And if you're adding x to z, but you're also is equal to adding y to z, then x has to equal y. And this is related to unification. It's sort of giving the ability to embed unification into the matching process, bringing this closer to Prolog in some sense. Another interesting pragmatic example is simplification of memory expressions. So many SMT-lib theories are expressible as form clauses, as sort of side conditions that need to be talked about. And here in particular, it's aliasing information about addresses that you need in order to simplify memory expressions. So here's a simple rewrite rule. If you select the address A, after storing at the address A a value V, you just reduce that to V. Okay, fine, that always works. But if you want to select after a store where you know these two are not equal, then you can also reduce. But you need to know those two are not equal and never will be equal. And so this sort of requires sort of the data log aspect of things. Aliasing analysis is a classic program analysis thing you can do in data log. That's an effective and succinct way of talking about it. And these are similar. And here we have an example where I have a slightly complicated store expression. If I'm selecting R1, this has to pass through this R0 knowing that R0 is not equal to R1. And it does. Yep, it figures out that it was the value V1 we stored there. And if you delete this, it no longer works. It doesn't have enough information to infer that actually it's able to push that thing through. Another very interesting application is equation solving. Sort of the high school picture of how do you solve equations is you do the same things to both sides of an equation. And you're doing that often to achieve variable isolation. And then when you have an isolated variable, you substitute back into expressions. Now the eGraph already does this substitution process for you, because that's just how it is. It's just doing all substitutions all the time. And then finally, you can extract terms without unwanted variables as a way of extracting the solve for terms. So here, if I know x plus y is equal to z, then I know that z plus the negative of x is equal to y. Again, this isn't really a rewrite rule. It's finding an equality, chewing it up, and turning it into a new equality. And then I have some simplification rules involving negation. And you could intrinsically say, like, give me an expression that doesn't involve variable x, but a way to hack that in is to isolate just a big expression, and then you'll just find a small expression that's equivalent to that big expression. So if I wanted to solve for this, I insert this equality into my database, and then it runs, and then I ask for an equivalent thing to my big expression, and it figures out that it's equal to negative a. And that is correct because there's a c on both sides, those cancel, you move this a over to that side, it's negative a, and my big expression is negative a. And very quickly, some other, as computer scientists, reflection is fascinating at all points. And you can reflect the graph equality into a predicate equality or term equality, which, if you know it's true, if it's in the same E class as true, you can reflect it back into the native E graph equality and vice versa. And so what this enables you to do is you can talk about EQ of A, B in the absence of knowing if they're actually equal to each other. If they're actually equal to each other, it'll be an E graph. If they're not actually equal to each other yet, you don't know they're equal, then maybe you need to chew on it with the Boolean algebraic reasoning to actually determine that it's equal to true, and then you can reflect it back in and do all the substitutions all at once. And quickly, another fascinating example, and sort of what brought me into this, is it gives you the ability to express uniqueness quantification, which is a common thing you come across in universal constructions and category theory. You can Stolomize exponentials to turn them into Horn clauses, and then the uniqueness property here is sort of naturally expressible in A log 0, because you need to build this equality on the right-hand side here. There's some more examples down here in this drop-down box that go into deeper detail of proofs of all that. And so that's it. And thanks. I've had many discussions with many people, and their ideas have sort of filtered into all of this. There's related work, relationally matching, egg-like, which Young is how to lay down some truth about, souffle egg, and SMT multi-patterns is somehow related to all of this also. So thank you.
We have time for one or two questions.
Yeah, I'm shocked.
I have a question. I am shocked. This is definitely the best ASCII talk I've ever seen. What's the point? Well, this is really cool, and what, I feel like the traditional use for quality saturation and egraphs is either in sort of theorem proving environment or an optimization environment. So, where do these really cool examples, how do they fit into those sort of applications, I guess? If you could repeat the question.
Well, how does this fit into traditional uses of egraphs?
Yeah, or quality saturation.
Or quality saturation. I just found that the extended ability for guards, but also new predicates to guard rules to be really, really useful. And data log on its own is extremely useful and extremely powerful and compelling because it has an efficient implementation, which is super important. It's really important to be efficient. And a very declarative, very beautiful. And so I think what this comes down to, the most compelling thing about all of this is program analysis. That if I want to do egraph rewriting and program analysis, data log is the appropriate tool for program analysis. It just feels like it should all come together. And then also, personally, I'm very interested in the improving aspects, so that's actually why I started working on these things. I mentioned the category theory problems, or brought me to this idea.
I think I'll cover this one more. So let's go over yields.
Could you comment on the relative strengths of adding quality, maintaining quality variance in data log? So solve data log and then you add some quality variance to the internal representation correlation versus adding multi-facets to A, because the end result is the same, and you have the quality and horn clauses, but the egg setup is very different, and then you're going to have iterations of quality saturation versus traditional data log implementations with matching sets and stuff.
Yeah, you threw exactly the question I want to hear. So I've been sort of fixated on data log for a year or so.
What was the question?
Oh, sorry. How does this relate to traditional data log systems where you could just inject maybe a new equality into those systems? Or maybe, in fact, you can embed all of this in traditional data log just using an explicit equality predicate. if you already have terms in Datalog. So I've been experimenting with Souffle Datalog a lot to try and talk about these ideas, and also the a group has been on parallel lines exploring these ideas. In fact, there's Remy has this talk here where he talks about trying to embed egg into souffle in various ways. And basically, until very, very recently, I had never seen an embedding into souffle that got anywhere close to the efficiency of using egg. So I initially became sort of discouraged. I started actually using souffle and not doing this. I became discouraged and feeling like, why am I trying to beat egg at its own game? Doesn't make any sense. And then I built this. Very, very recently, I think I have an encoding that seems to work pretty decently in Souffle. It's very hacky, and it involves basically taking all of the insights of egg and just trying to transfer them, more or less, like in the Souffle context. So basically, the short answer is that if you just try and hack this into Datalog, and Souffle already has a notion of equivalence relation back that you find that isn't enough. It's too inefficient, basically, to like do this without deep ideas from the eGraph implementations and community. But this is, I call it egglog 0 for a reason. These are ideas being explored.
I think we'll have to leave it there, so let's wrap When you're done speaking on Gather, make sure to step off the virtual stage as well as the real stage.
Have you been doing accounts? No. Okay, sweet. It's good. Can you go screen record?
Yeah, the blocks and oh my
No,
god.
you have to restart.
I can see it here.
Okay, so I'll get started. I'm Yihong, and my talk is titled Chasing an Egg, and this is summarize some of recent work on building a relational graph. And so let's get started. So let's first look at a typical workflow of equalization. So we start with some input expressions, we insert it into an e-graph, and then you will do some pattern matching on this e-graph based on some variables. And this process is called e-matching. And if you have multiple patterns to be matched simultaneously, then this is called multi-patterns, which is an extension to e-matching. Okay, and then you apply this match you found during the pattern matching, during the e-matching. And during that process, some classes will be created, some will be merged. And during that process, you need to obtain an additional value, which is e-class analysis. So e-class analysis are values associated with the e-class, and they will be created, propagated, and updated during the e-class updates. Okay, and now you get a new e-graph, but it's not valid because some of the invariants are broken. So what you need to do is you need to restore the invariants. And that process is called conversion. So basically you need to maintain the congruence integrity of the e-graph. And then you get back to a new e-graph again, and you apply this algorithm again and again, so iteration after iteration, and you fix point or timeout, and finally you extract your optimal expressions. So this is the workflow of equation. So what are some limitations of the current e-graph frameworks? So the first is with too expensiveness. So for one, patterns are hard. They are not supported until very recently, I feel, and but their support is not very optimal right now. Moreover, non-equational reasoning is very hard. So e-graphs are good at this equational reasoning, which is if A is equal to B, then B must also be equal to A. But it's not good at this non-equational reasoning, things such as implication relation. So for example, if A implies B, then B does not necessarily imply A. And that kind of reasoning will be hard to do in an e-graph. Okay? And performance-wise, there are also some limitations. For one, imagine slow. So imagine the bottleneck of many different applications. It takes the majority of the runtime. Moreover, imagine the backend work. So if you look back at the workflow of equalization, you see that the imagine is done from scratch in each iteration. So this means that some of the patterns that have been discovered before will be discovered again. So this duplicates work. There's some work on incremental imagery in the literature, but it's even harder, and it may not work in the case of equalization where the graph moves very quickly. Okay, so how can we overcome these limitations? Our direct work on relational matching gives us some clue. So in that work, we just treat an e-graph as a relational database, and the imagined pattern comes out naturally as relational queries. And just with that, we are able to achieve a symptomatic speed up and the new compacted bound, as well as the optimal algorithms that achieve that bound. Moreover, we have very easy support for multi-patterns, because multi-patterns are just a concatenation of several patterns, and you just concat them in the relational queries. So this also very good, but relational imaging is not used anywhere in AD or any other existing e-graph frameworks. So why is this the case? So let's look back at the workflow of equalization, but with relational imaging. Again, you start with some input expression, you insert it into an e-graph, and then you need to convert this e-graph into a relational database. And then you build indices on this relational database. After that, you can run your relational queries. and then you apply the match, you restore the invariance, all of them are done back in the original equals. So you'll see that here we have two representations, and we need to convert it between these two representations, and this is company, and this is also part of the reason why relational imaging is not implemented anywhere. So what we want instead is relational equals. We want to build a whole equals relationally. What that means is that once you insert your input expression into the equals, the equals itself is our relational database. So it's both our relational database and an equals. And you can directly run your relational queries on this relational equals. And you have your mesh, you restore the events, all of them are done on this single representation. So you see that here we only have one representation, and there's no cost associated with converting back and forth between different representations. So this is very nice, and this is what we want. So motivated by this, we build AggLite. So AggLite is basically equals on top of SQL. So we translate the standard equal operations like insertions, rewrite, and rebuilding into SQL queries. So basically, we support the acceleration. I did some early benchmark, and it's an auto-compute lot of egg, which I think is a promising indicator. Given all the overhead associated with industrial relational database system. Okay, so let's see how concepts in an egraph translate to the concepts in a relational database. So in egraph, we have congruence. So this means that for every add expression, its two children, A and B, will uniquely determine its because ID, which is C. And you can write that relationally. So here in the relational form, we say that if you ever see two items with the same A and B, then their C must be equivalent. And we have a name for that in relational database. This is called functional dependency. Similarly, we have variables in equals. So here this is associativity, and we can write that relationally. Here we introduce the existential quantified variable, which is BC, to denote the ECAS ID of B plus C. And we also have a name for that in relational database. This is called tuple generating dependency, which generalizes data log because you allow this existential quantifiers. And in fact, both functional dependency and tuple generating dependency belongs to a broader concept, which is called data dependency. Therefore, we can claim that equals or relational equals are about data dependencies. Therefore, we can also say that equalization is just a special form of the chase. So what is a chase? The chase is a family of algorithms developed in the database community for reasoning about data dependencies. So the idea is very simple. You just apply all these dependencies until fixed point. Therefore, these standard optimizations like semi-naive can be applied. And semi-naive basically incrementalize the evaluation of data dependencies. Therefore, we can also say that equalization is just a restricted kind of the chase where you have efficient evaluation and your solution has nice properties. So we have AggLite, which is very nice, but it's not practical enough. There's two reasons. One, we didn't consider incremental imaging, so this is also a problem we didn't consider in our previous work on relational imaging. So imaging still duplicates work. The second is ECAS analysis. So this is also very important in practice because many practical applications use that. So how can we overcome that? The first issue is relatively easy because from the dialog perspective, it's just semi-naive evaluation. So you can just plug semi-naive evaluation in and you get incremental extension for free. The second issue is slightly harder, but sampling people have figured out. So there's a PLDI 2016 paper on the lattice semantics of dialog. So in that semantics, basically a tuple is viewed as a function from the domain to a lattice. And this lattice is the standard Boolean lattice, and this is exactly the semantics of dialog. We can also extend that to other lattices. And this precisely captures the monotonic nature of ECAS analysis. So just plug that in and you get ECAS analysis in relational form for free. Okay, so with that we have this very nice, elegant correspondence between concepts in egg and concepts in our relational egraph, which is called XSharp. Let's summarize the talk. So we map concepts in egraph into its corresponding relational form. So congruence is mapped to function dependency, rest is mapped to tuple generating dependency, and ECAS analysis are mapped to the lattice semantics of dialog. With that, we can mitigate many of our previous limitations. So for example, multi-patterns are hard. Well, in dialog, all the patterns are in nature multi-patterns. So, and our language is a superset of dialogue. So we support these patterns very naturally. Second, non-equational reasoning is very hard in epochs. Well, because our language is epochs is superset of dialogue again, and dialogue is good at all the kind of different reasoning, which includes this non-equational reasoning. So we also support them very easily. Performance-wise, imaging is slow. Well, we have regional imaging, and we can do this regional imaging without the cost of built indices and without the cost of converting back and forth between different applications. So this is very efficient. Finally, imaging duplex work. Well, from the dialog perspective, it's just standard naive deviation, which is standard in the database literature. So with this added expressiveness power, we gain a lot of we can do a lot of cool applications with that, and these are not expressible before. So do I have time to go to maybe one example?
Yeah, we have a couple minutes.
Sure, yeah. So yeah, maybe we can go through the non-equational reasoning example. So here, so you see that for the diagonal rule, like on the right-hand side of both sides, the diagonal rule, which is it reads as this. So for every term that is the absolute value of x, we span a new term, which is x is greater or equal to value. And so we don't know if this term is true or false. But if this term is merged with the true item, then we can simply say that the absolute value of x is equivalent to x. And we can have a mini theorem prover instead of our regional epoch, which is the first rule, and there are also some other rules. With that, we can use our mini prover instead of our regional epoch, and use that to prove some of theorems that are not proven before, and we can use that to add our rewriting. So this is very cool, very powerful. And with that, this concludes my talk, and I'm happy to take questions.
I think we should maybe save questions for offline if you want to be convinced that you guys should just get along, chat with Phil or chat with Yvonne. I think we should move on to the next speaker, which is Nadia, I believe. The next set of talks will be convincing us that instead of egraph and data log, it should basically just be tree automata instead. So these next pair go together as well. So yeah, go walk on the stage.
Can you unmute your gather? Yeah.
It's good? Okay, awesome. Cool.
Everyone go together. Okay, I'm just looking at it.
Ta-da!
There we go.
Awesome. All right. So the joke title of this talk is is that we got something that's better than egraphs and coding, but this was just to catch your attention. This talk is actually not about egraphs at all. So this talk is about this new data structure called equality constraint tree automata. And this is mainly the work of Jimmy Kova from MIT and my student Jane Guo. And I'm just a messenger, so don't throw me. All right, so what's the goal? So the goal of this whole ECTA work is to be able to compactly represent large term spaces And at this point, you're like, we can already do that. eGraphs already do that, right? One of the main differences that we want to add constraints to these term spaces, and I will tell you in a second what I mean by constraints, right?
Nadia, can you stand closer to your laptop so the remote can hear you?
Closer to the laptop. Better?
I think
Okay.
so.
And then once we represent this, compactly represent these constrained term spaces, we also want to efficiently extract or more generally enumerate terms from that space. And by enumerate, I mean extract multiple. All right, so I will first show you an application for why would we even want to do this. And then I'll try to explain to you what the ECTA is using an example. And if we have time at the end, I'll tell you about our algorithmic insight, but if you don't get there, no big deal. All right, so why did we start doing this? Our main application right now is in type-driven program synthesis. The idea here is that you have like a big library that is kind of hard to use, and so the programmer has in mind the types of things that they have and the types of things that they want to achieve, and they submit this type query to the synthesizer, and the synthesizer searches how to compose the library functions together to get you a thing of the right type, and gives you some ranked list of possible solutions of the right type. Okay, so for example, let's say I'm a Haskell programmer and I want to apply some function n times to some initial value x. I can express this problem as a type query. I want to say I have a function f of type a to a, and I have some initial value of type a, and I have a number of times n, that's an integer, and I want to get something of type a, right? And so then I shove it to my synthesizer, and hopefully we get a solution. So let me just show you very quickly how this could work. This is a type-driven synthesizer called Google Plus. So this is using our work in the backend. So here's the type query that I showed you on the slide. It's very small. Let me make this bigger. Okay, and then I press search. Hopefully it works. So it starts spitting out some solutions. We don't really have time to go into this, but believe me that this first solution is not what we want, and we can tell that by the example executions that it's giving us, right? So it basically says if you apply increment function to 0 2 times, you get 1. That's not what we want, right? But this second one is actually what we want. And so here, what the programmer didn't know is that the Haskell standard library has this function iterate that returns an infinite list that's applying this function, every number of times to x, right? So this is the motivation, right? So we want to be able to do this efficiently. And so in our prior work, we already implemented one algorithm that does this. And this work was called Google Plus, and it used NSNT-based encoding to do the search, right? And so in this work instead, we implemented a whole new backend search engine for this Google Plus tool using this new data structure ECTAs. And one upshot is that the original implementation was 400 lines of code, 4,000 lines of code, and this new one is only 400 lines of code. So it was massively easier to implement type-driven program synthesis on top of ECTAs. But also, if you look at the results, we ran it on the original Google Plus benchmarks, and not only the new guy solves more benchmarks within some timeout, but also if you compare the solving times for the same benchmarks, it's 8 times faster on average. So it's much faster and much better using these ECTAs. All right, so what's the secret sauce, right? So how does that work? So I'll use the same domain of type-driven program synthesis to illustrate ECTAs. So the question is, how do we compactly represent the space of well-typed terms? And let's do this kind of step by step. Let's start with a very simple setup where we don't actually have any types, right? And so instead, we just have some unary functions, let's say f and g, and some nullary symbols, nullary variables, like scalars, like x and y here. And we want to represent all applications of the unary symbols to the nullary symbols, right? So to do this, we can use a good old tree automaton, right? So what is this tree automaton? Well, it has these round things are states, and these rectangular things are transitions, and the double circle is the root or acceptance state. And so, since you're familiar with E-graphs, I think the easiest way to understand what tree automata are is in terms of, by relation to E-graphs. So you should think of states as E-classes and transitions as E-nodes. Except that the main difference is that we're not trying to represent an equivalence relation, we're just trying to represent a set of terms. So the fact that F and G both belong to the unary state doesn't mean that they're equivalent. It just means that they're two things in the unary state, right? And so how does this guy represent our terms? Well, so if we pick a run, an accepting run of this automaton, right, that would correspond to a single term. And what's a run? Well, basically you just pick one transition for every state, right? So here for unary we picked F, for scalar we picked X, so we don't have X. And here this dollar transition is application. This is how we say application. Deal with it. Okay. But what if we have types now, right? So now that same, let's say we want to represent a subset of that same set of terms, but only the well-typed ones, right? So we want to somehow modify our tree automaton to rule out the ill-type applications, right? So the first step, we will add the type information into the tree automaton so that we can even talk about types, right? So far it's just, again, plain old tree automaton, but we will annotate our variables with their types. So for the unary functions, we will say it has some input type, it has some output type, right? And then for the scalars, we just say unary. Okay? So now we want to restrict the set of accepting runs to only well-typed terms. How do we do that? And this is exactly where ECTAs come in, right? What is an ECTA? It's just a tree automaton plus some equality constraints. So to restrict the set of accepting runs, what we're going to do is we're going to add an equality constraint to our application node to say that the run is only accepting if the input type of the function is the type of the argument. So basically saying that the type of the formal should match the type of the action, right? So that's all it is. It's just tree automata plus equality constraints. And the effect that it has is restricting the set of accepting runs, right? So for example, this run that picks F for unary and X for scalar is accepting because the input type of X is int and the type of, of F is int and the type of X is also int. But this one that picks Y instead for scalar is not accepting because the type of Y is car. It doesn't match the input type. Okay, so these were very basic types, but now I'm going to show you something really cool, right? So what if we want polymorphic types? And we'll start with like a very basic kind of polymorphism, but we'll look at it in a second. So let's say we have another function h whose type is for all a to a. How do we represent that in our ECTA? Well, you see we added this new function, but you probably know as you are dealing with E-graphs that all kinds of variables or bindings and things like that are really hard to deal with in these data structures, right? They create little problems. So instead of explicitly representing the type of age using some kind of binders, like the type variable a, instead we will add this new state that I'll call any, that represents any type. And in this case, it will represent all types that the type variable can be instantiated with. And why I said basic polymorphism is, for now, we just assume that it can only be instantiated with the basic types, int, bool, car, right? So that's why the state has, is connected to these three transitions. And now we can connect the input and output of h to any, right? Are we done? Not really, because this represents the type a to b, not a to a. Okay, so that's kind of the point of variables, that they can tell us that two things should match, right, inside the type. Well, but we have constraints for that, right? So all we do is we add a constraint to h saying that the input type should be equal to the output type, right? So this is a sort of like you can think of it as a nameless representation of binder type variables, right? And sort of a reverse to Brown notation in a sense. You can talk to me after we talk about this. Okay, and how do we go from that very basic polymorphism to like full Haskell types, right? So this is actually very simple. So first of all, we want our any state to not just represent all basic types, we actually want it to represent all types, right? So for this, we will use cyclic ECTAs. So no surprise, ACTAs can be cyclic, just like eGraphs can, and just like regular tree automata. So in addition to like things like int and bool and char being children of any, we can have list of any also being an any, or we can have a function from any to any also being an any. So now we can represent both things. And finally, we don't like this like scalar unary distinction. That's kind of annoying, right? We don't do that in higher order languages. So we will represent all our variables uniformly. So just like x had a type, similarly our functions, even higher functions like map, will also just have a type. So in particular for map, its type is an arrow, whose input type is also an arrow from any to any, and whose output type is an arrow from list any to list any. And of course, we just add constraints to say that the A's and the B's inside the map type should match. Right? Makes sense? And then with that encoding, we can build an CTA that represents all well-typed terms in a higher language with polymorphism, up to a certain size. Do you have any more time?
Go quickly.
All right. And so now I showed you how to represent all these constraint term spaces, right? But now we actually want to be able to remember our original application. We actually want to be able to quickly extract some terms that satisfy the constraints, right? Or enumerate a bunch of terms that satisfy the constraints. And kind of long story short, if we just enumerate the runs of the tree automaton and then check if they satisfy the constraints, that's not going to be efficient, right? So if we take our, this was the one with the H, right? If we just start enumerating a bunch of runs and checking, this is going to be not going to scale, right? Because only 4 out of the 22 runs of the underlying tree automaton, only 4 actually accepting runs of the constraint. Only 4 satisfy constraints, right? So instead, we want to do this efficiently. And so the main idea is that we don't want to eagerly enumerate those constraint states. Instead, we want to do it lazily. We basically use something like a unification variable to do it. So essentially, if we want to enumerate this automaton here, we start top down, right? Basically picking a transition for every state. But so far, our states are not constrained. So that's fine. We're just picking eagerly, right? But as we are going down, we are propagating our constraint also top down, introducing fresh variables to be able to account for the parts of the constraint that is out of scope. And so these little constraint fragments are just propagated down like this. But so the interesting thing happens here when we have to enumerate state A1, which is a constraint state, right? So here, instead of picking, should it be int or bool or char, which would be really silly to do now because it would probably not work out and need backtracking, right? Instead, we just suspend the state. We basically introduce this unification variable v1 and just move that part of the automaton there. And then as we enumerate A2, we see that it's constrained to be equal to v1. So what we do is we take A2 state and just intersect it with what's already at v1, which at this point doesn't have any effect because they're the same, right? So this is what happens. But now when we get to the type of x, which is also constrained to be equal to v1, now we intersect the type of x with the state that's at v1, and now that has the effect of removing the extra types that wouldn't have matched the type constraints, and we are only left with it. So basically, we managed to find this well-typed solution without doing any backtracking, just by doing these unification variables. That's all I wanted to tell you today. So thanks.
Really cool stuff. I have 2 related questions. How do you represent type classes and how do you represent bounded polymorphism?
Next speaker is remote. How do we
just
Right,
same type, get them to?
Do we have speakers in the room?
Like
how do we get them on the screen?
We can plug in.
We can plug this in. Okay.
By bounded polymorphism,
I can do it. Is that okay?
Yeah.
Here. Will the audio work?
Well, okay, maybe that's not relevant because you're with type in Haskell.
That's a good question.
Audio work?
Because there used to be a cable there, right? Like that you can plug into the laptop.
Do you know?
But that is
I'll check.
also related
Let's
to
try
type
it.
classes, right? So I bet we can do, I mean, we haven't tried this, but I suspect we can do similar encoding.
I think we may have to take the rest of the questions offline so
Okay,
we
no worries.
have time.
And you can encode SAT into this.
Okay. All right. So the next speaker will be the next speaker will be joining us remotely. So we just need to figure out how to put him onto the screen.
I need to rejoin, so I'm there.
I can hear you, Remy. Is it? Can you guys hear Remy at the back? Remy, say something.
Can you hear me?
We're having to use the. Keep saying some stuff, Remy.
Are you gonna start my talk right now? Alright, so I'm gonna practice and just interrupt you already. Okay. So my name is Remy. Today I'm gonna talk to you about graphs, math, and intellectual pieces. Right. So I have a quick audience, which I'm not going to show the answer now, so that you can discuss later. So I'm gonna jump to later slides and then show you some really beautiful e-graphs. So here we have the e-graph and some before. Should I keep talking or should I start?
Just start over and full screen, and you're good to go.
Great, cool. Can someone also hover from the audience? I want to test if I can secure it.
Hello. Hi, Remy. I don't think you're going to be able to hear them.
All right, okay. So you don't have the president like you, and I can't hear you laughing to my jokes either. But I'm sorry. Do you see my full screen?
Yeah, you're good to go.
You can close the chat.
Okay, thank you. Yeah. All right, so this is another talk about the automata. So if you didn't completely understand last round, you might understand it a little better this round. This is joint work with James Hubble, Alton Tan, and Doug. So report into receipt, which is cancelled. Now, which is the question side. Now we have terms. We have variables x variables, y variables, and we have the function f applied to them. Right. So the question is what would the e-graph look like if we insert these terms into the e-graph? So it's a concept question because the e-graph is really simple. Here because we didn't assert any equality yet, the e-graph basically has a single thing per class. Right? There's nothing to it. Right? So what we're going to do now is that we assert all the x variables are equal, and then all the y variables are equal. And then to reflect this change in the graph, we're essentially going to merge all of the classes of the x variables, and similarly all the classes of the y variables, which I do now. Right? So there's more. So because we know that
Remy, hold on 1 second. We're having some audio issues.
Serious AV.
Okay.
No.
Just tell the AV system couldn't keep up with his pace.
Jesus.
Rockstar talk. Yeah.
No? No audio coming over that. What is playing?
It's a sunspot.
Yeah.
Okay, all remote talks are good.
Wait, so why don't we just play some of that? I cannot change anything since starting is coming.
Just use Zoom.
Well, like, we still can't get the audio here. Like, there's no way to connect to it. No one knows how the computers work. Yeah, can we turn it off? We don't have to. We need to figure out how to get a remote speaker to the room. Audio, yeah. Yeah. It's just the audio. We have the video figured out. I need to get my laptop down. Later on, speak. We didn't know where to get down. We left down to
Something. Okay, you want me to turn off your mic so that I don't hear my own voice?
Our mic is off.
No.
Alright.
Okay, I'm turning off.
Alright. Thanks. Alright. Okay, let's get back into this. Thanks so much for coming to the opportunity. Okay, so let's get back into this beautiful e-graph. So we union all of the x variables and the y variables. So now we notice that all of the f applications are not counted because they're applied. Well, these applications are not counted because they're applied to the same e-graph. So we basically union all of the applications over here and over here separately, and then we duplicate. So now we just have one single e-graph. So this is the classic observation that congruence can sometimes compact the e-graph. So let's go back one step to this graph. And then instead of saying that these variables are equal, what if we say that these applications are equal? Right. So now what do we do? So what's going to happen is that now we can only unify the classes containing the f applications, and that's basically pretty much it. So under certain circumstances, in Turkey, we can still compact it a little bit. So now I'm going to tell you that this f function is actually the predicate even that tells if the input is an even number or not. And then these variables are actually integers. These are odd numbers, these are even numbers. So ideally, suppose we're only able to observe the output of the even predicate. Ideally, like all of these odd numbers are equivalent, right? We don't care which odd number it is, so we only care about this output false. And similarly, so all these even numbers are also equivalent. We don't care which number it is. We only care about output true. So there's this notion of observational equivalence that is a little more general. So you can, in a sense, think of it as kind of a code function. All right. So can we take advantage of this observational equivalence to also make the feedback even more compact? All right. So this is our goal for the rest of the talk. So so let's go back to focus on the odd numbers. We can look at how we go from here to the bottom to here to the top. So just like every single problem in computer science, we solve the problem by writing a reference code. So I hope you're laughing right now. So the first step is to write these. Right. So this is going to be a little actual confusing. So bear with me if you can talk. Right. So the first step is to write these terms as strings. So 1 even is going to become 1e. 2 even is going to become 4. 3 even is going to become 3. Right. So it's 3 by the terms. It's not possible in general, and then we're going to write the correct instruction for the
Should we ask him to stop his speaker?
Right. So what we do is that we
Ask Yesu to stop his speaker, maybe.
saying that we make a choice among all of these instructions. So it's either 1e, 3e, 5e, For this top class, we have this a little smaller bracket that says that we first choose one of 1, 3, 5, 7, and then we say that's it.
Remy, you're echoing. So can you turn off your speakers?
Turn off my speaker.
It's something to do with the number.
Yeah, so we have these two brackets. And then the next step we're going to involve. So by the way, this takes me out. So we're going to draw the final state of the for each bracket. So here's what it looks like. So one output like this is the first bracket. So we have the assumption. We have this space. First second input 1 and closing space is 8.
Turn off the speakers and chat. This is still on. No, he's the one who's. The microphone has to be on, right? No, it's a speaker sign. Yeah, it's a speaker sign. Maybe the speaker sign should be switched off.
No. Then his audio will not come, right? Because
no, the microphone. His microphone is working, right?
the speaker sign comes whenever someone is on those orange spots. It's not a function.
Okay.
What?
You can't stop it. You can't stop it.
What happened? His speakers are off, so now he cannot hear us.
Okay, just boot him. There's no alternative.
Yeah.
Poor guy.
I think we just have to proceed with the in-person talk. I don't know what else.
Where's the feedback? But the people in
It's on his side.
Gather won't be able to. I mean, he's on an orange square.
There's two.
You can mute him.
Well, if I mute him,
Is the feedback all coming from his?
I think it's on his side.
So yeah.
Yeah.
So it's problem. There's nothing you can do on this side. We can't stop him. It's unstoppable.
How come we can't stop him? No. Oh.
No, I don't think.
Is someone else on Gather? Is audio, does he sound functional, someone else? Yeah, can you get on Gather?
It's pretty bad in
No.
It's not good, Gather.
Okay. You gotta skip running. Alright, well, who's the next topic?
Yeah, everyone else is muted and Gather, so it's not someone else.
It's his mic. That's the guy. I feel bad because he seems to be doing the entire talk, but no, I think if he can boot him off the gather, he'll know that he's not giving the talk. I think he's like full screen share talking to us. He'll know. Okay. Yeah.
Oh, you turn on the speakers.
Remy, unfortunately, can you hear me, Remy? Yeah. We're going to have to skip you and proceed with the in-person talks. The in-person audience atrocious for some reason. Okay. So, it's alright. It's alright. Alright. Yeah. Yeah, please just go ahead and get started.
Siddharth, but I think so because he was speaker, so the next person photo is
This is work. Do they use the mic or should they just talk down?
You can just talk about the mic should
use the mic.
Yeah, let's not tempt fate.
Okay. Yeah, just project.
The mic works.
Okay. Please use the mic.
The mic helps.
Smash it. Drop kick.
Yeah, thanks. Right, so, hi, I'm Andres. I'm gonna talk to you today about
saturation as a tactic for proof resistance, which is joint work with Siddharth, who's on the picture. He should be around, but apparently he skipped the session. But you're gonna find him as well. So I suppose that people here know the egg part and the equality saturation part. So I'm gonna start with the other part of the title, tactics for proof resistance. So when I'm talking about proof resistance, I mean like what's normally called as interactive proof resistance. And specifically, I'm going to be talking about the lean theorem prover here. And we're going to show more or less how that kind of looks like. Here, so what you can see here is like we can write mathematical theorems as terms in this language, and so here you can see like the theorem on the left hand side, and on the right hand side is the interactive part. So this is like a small screen cast of that. So you can see here, these are some simple things about groups, and so we're showing like, for example, that multiplying with the inverse on the left will cancel out on this theorem here. And then the way we normally do is you have these group axioms like associativity of multiplication and stuff like that, and you can apply them as rewrites. So these rewrites are called tactics. And on the right hand side you can see the what's called the state of your talk, of your proof. So you have your goal, which is after the turnstile, that's like we want to prove this equality, and then you have your context, which are like the variables you have there. Like for example, this group alpha means that this thing is a group, and A, B are elements of this group alpha, etc. So it's interactive because you can actually, when you apply the rewrites, it'll do the rewrites there, and we can apply these different things until we actually end up showing equality on both sides, and it'll tell us, okay, the goal is accomplished. But there's also some automation involved in that. So if you see here, there's this simplification tactic that will take multiple rewrites and try to apply all of them. And we used the try here because it will not succeed, because these rewrites don't work. Like if we just apply the rewrites that we have here, it won't work because the associativity of multiplication has to be applied in the other direction. So I have to use this left arrow here to show that it's applying it in the other direction, which essentially means in this context, rewrites are very much directional. Even though they represent equivalence, they very much are directional in nature. So that's where these equality saturated, or E-graph tactic, equality saturated is probably a misnomer there, but comes into play where we can use E-graphs to actually get around some of these issues and make these automation more useful, or more powerful rather. And so I'm going to show you how this works as a tactic. So what you see here is like the piece of the buffer that we saw before, where we have the context and the goals. So this is the local context of the tactic, and there's a goal of a tactic always as well. And so we'll write this tactic around these. And the idea is that we also want to have some rewrites, which will be somewhere in the context. You'll usually have them declared, or for now we're passing them explicitly to the tactic. And out of the local context, we want to instantiate some of these rewrites, and I'm going to talk about in a second how we do that. But then we can take the rewrites and the goal and pass them to A, so that it tries to do equality saturation on them and find some rewrite that proves the term. And then we get an explanation of A, like applying which rewrites gives us the transformation the full rewrite that proves the equality. And then we can take that explanation and take it back into the theorem prover, in this case lean, and construct a proof term out of these rewrites to have proven whatever equality we're trying to prove here. So that's the basic outline of the tactic idea here. And I'm going to explain how we do these things more into detail. So one of the main points or advantages of egress is that, as we know, that because it's not destructive, you can essentially apply rewrites in both directions, right? So what you see here is some egress for a more simple term, like that's A multiplied with its inverse, and we want to show that it's equivalent to that this is 1. And so we can apply the rewrite that says A applied to its inverse is 1. And so we'll get the terms here, and this multiplication with 1 we could do in reverse because we have both equivalence classes here. So we can multiply by 1, but we can also so we can take a multiplication by 1 away, but we can also add it again. So that in that sense we get bidirectional rewrites automatically by using egraph and eclass. A caveat with this is, of course, specifically in this example, if we multiply by 1, we can multiply again by 1, and again, and again, and we'll get an infinitely growing egraph. So in this case, it is actually infinite. So there's a lot of times where like, so some rule we can get it encoded, but not always. In this case, we don't. But we don't care, it's heuristic. So we can just grow the graph to some size. If we find a proof, great. If we don't, then it's also good. We don't have to have all the so we cannot always do equality saturation. We don't have to have all the terms. Sometimes we have rewrites that are already like instantiated for a specific term, but sometimes we have like them quantified, like universally quantified over some variable, and so there are some things that work there and some things that don't. So for example, the rewrite that I was talking about before, if we multiply an element by its inverse, that becomes 1. That's great, we can use that. But how do we reverse that, right? Like, if I cannot just take 1 and get a to the minus 1 times a, because I don't know what a is, right? Like a is a variable here. Well, I think I have a typo. These should be question marks on the right hand side. If I try it with the question marks, I'll get a runtime error from egg. It's like, I don't know what question mark a is because it's not bound. Because it doesn't know what a to use. But that's where the thing comes, the context comes into play. We have some variables in our local context, so we can just use those to instantiate specific versions of these rewrites to get them also working in the other direction. So we had A and B in our context before, so we can actually just add rewrote rules for these instances of A and B for our concrete proof here. And so taking that back to like the lean world, right? So we're showing like this is how we take the local context and instantiate rewrites here. So we just have this universally quantified theorem here, equality, and we have these two terms A and B of type alpha. We can just instantiate those that we have in the context, because if we're going to find some proof, it's going to be with those, and just add those two variables, those two equations, and try and find rewrites with that. So that actually gives us a lot of power, but also can break, or can explode rather. So what if we have more universally quantified variables? For example, associativity, we have three terms, and so we actually have to do that for every pair of variables, and you can see how this can quickly explode a lot. So we would get a blow of variables, but it's heuristic. So we either come up with ways to just do some clever instantiations and not all of them, or we maybe don't find a proof if it's too many variables. Right. So if we put it all together, we can kind of get proofs like this, right? So this is like a typical example of the magic insights in some proofs where you have like you multiply by 1 and then convert by 1 into a product of inverse time itself, and actually show the like this kind of qualities from that. This is a handwritten proof. I didn't find particularly this one. I found a bit larger one, but it's the same. It's the same principle. Like in the end, it proves the equality of the two things. So it gives us a lot of power in the types of things we can prove with this as adaptive. But this is work in progress, so we haven't finished. It doesn't work in every case and everything. So currently we're using JSON to, like we copied that from Herbie, to talk to the egg, but Lean has a function interface. There's some problem with taking out the terms back from the explanations, so it doesn't work on all cases, etc. Like rewrites also work on logical equivalences in Lean. We don't have that yet, but that would make a lot of sense. Or combine this with other tactics and get much more sophisticated rewrite engines. So it's still work in progress, but I think there's a lot of potential in here. And there seems to be interest from the community here. This just popped up like a week ago, this issue here in GitHub. So yeah, in conclusion, we've seen like in theorem provers, this holds as well, that egraphs have a lot of advantages over the structured rewrites because we can do things in reverse. In tactics, specifically, because these are heuristics, we have a well-suited match for equality saturation. So we get a lot of possibilities to improve things here. And the goal is to get an egg-shaped hammer out of this tactic here. So yeah, thanks for listening. And I guess we don't have time for questions, but we can take those offline.
Maybe we can have one quick question while the switch is occurring.
Do you handle side conditions on any of your qualities at all? So like if you have some rewrite that has a condition on it, you know, like if this predicate holds the context, then you can do this rewrite.
I mean, you would get it as an arrow type in Lean. We currently don't do that, but it should be possible to do the same thing as when we're matching, because we're matching just types and the condition is a type. It should indeed work, in principle work, but we still haven't figured out all the method programming things for that.
All right, thank you.
Yeah.
Yeah, Hello? Hello?
You're good to go?
Yes.
Take it away.
Let me just. Alright, cool. We'll just start presentation. Okay, cool. Perfect. Hi everyone. I'm pleased to present this presentation on towards optimizing certified programs by proof rewriting. So I know that we're getting quite close to lunch, so I'll try and be brief. So without further ado, let's write a program. Now the program that we're going to be writing today is a function to free a linked list. So something pretty straightforward, shouldn't be too difficult. Okay, so let's see. Our function listFree should take in as input a pointer x, which represents a linked list. Now the first thing that we'll have to do is condition on the value of x, in particular on whether x should be null or not. In the case that x is null, represented here by 0, then we know that we've been given an empty linked list, and so in order to free it, all we have to do is return. Now, in the second case, where x is not equal to null, then we've been given essentially a console, where a block of memory of length 2 on the heap, where the first element is the head of the linked list, and the second element is the tail. And once we have this, in order to free the linked list, we can first recursively free the tail, and then once we've done that, we can free the console itself by calling free on. Okay, so problem solved. But are we sure? I mean, why exactly is this function correct? I've given you a sort of intuitive explanation of the logic behind its implementation, but why exactly? But I think actually we can do something a little better. So you know what? Let's write a proof. So if we want to prove the correctness of our function, we first need a specification, and we can do this by means of a fairly simple for triple in separation logic. So the specification that we'll be proving our function correct to is the following, which says that list free, when given a pointer x, which represents a linked list on the heap, that's the lseg xs predicate, where s represents the set of elements in the linked list. Then after executing, the function is guaranteed to return an empty. In other words, list free does indeed free the linked list. Now the majority of the work in this specification is done by the lseg predicate, which is defined as follows. Now, kind of looks a little bit complicated, but it's not too bad. We can break it down by looking at a simple concrete instantiation. So the lseg predicate consists of two cases. The first case is the case in which x is null, and this represents the empty list. And so it asserts that the heap is empty and the set of elements in the list is also empty. And this corresponds to the last element in a linked list chain. Now, the second case, when x is not null, represents a constant. So it first asserts that x points to a block of memory of length 2 in the heap, and that the first element of this block is a value v in the linked list, and the second element is a pointer to the tail of the linked list, encoded by means of a recursive occurrence of the lseg predicate. Okay, and so now you can see that through various instantiations of this predicate, we can represent arbitrary linked lists. Okay, so with this specification in hand, let's get about proving the correctness of our program. We can start off by setting up our heap state to be as described by our precondition. Now the first thing, and now we can step through our program. So the first thing we need to handle is this branch, at the outermost branch of our program. Now, as it turns out, this branch corresponds exactly to doing a case analysis on the lseg predicate by means of an open rule. So the open rule constructs a sub-proof for each case of the predicate that we're doing an analysis on. In the first case, we learn that the heap is empty and x equals null. And so we obtain a heap state that is equal to our postcondition. And so we can complete the proof by just using an emp rule. Now, in the else case, when x is not equal to null, we learn that x is actually a consel, which points to a block of memory with a head h and a tail t. And so now, the next step we need to evaluate is the recursive occurrence of list free. And we can do this by means of a call rule on t, and passing in and framing in the lseg t s1 heaplet in order to satisfy the precondition of our recursive call. And once we've done this, all that remains is the consel in our heap state. And we can eliminate this and also execute the free rule, the free statement, by using a free rule. And now, once again, we're left with a heap state that is empty, that matches the postcondition, and so we can complete our proof using the error. Okay, so done. Now we've formally verified our program to satisfy the specification, and we can be fairly certain that we've we've actually implemented it correctly. Just as a brief aside, this whole process that I walked through is just a reformulation of some insights from some previous works. Most recently, certifying the synthesis of heap manipulated programs, where we showed that we could extend a deductive program synthesizer, the Sosek program synthesizer, to generate both, given a specification, we could generate both an implementation and a proof of correctness an independently verifiable proof of correctness in sort of the Coq proof assistant that could be used to verify that the program holds this. Okay, so we're feeling pretty proud. We've verified this program. Looks pretty good, but unfortunately this is where problems start to creep in. So the old aphorism goes, the only constant in life is change. And nowhere is this more true than with code. And as it turns out, this can be rather annoying for practitioners of formal verification, such as ourselves, as we will shortly see. So let's have a closer look at our list free function. Now you may have missed this, but it's got a small bug, in particular in these last two statements. The issue is that our function is not stack safe. And now the fix is fairly straightforward. All we need to do is permute the last two statements, and now we're done, and the program is stack safe. But what about the proof? So the problem is that our proof no longer holds for the new program. And so we have to throw away all the effort that we put into verifying the original program. So this is the kind of core concern that spurns the work that we're looking into, which is, what if, rather than going through all this strife, we rewrote the proofs and the programs together by first doing the transformations on the proof tree, and then extract it using a Susslik extraction mechanism to extract both the optimized program and the updated proof together. And to do the rewritings on the proof trees, we can use egraphs. Okay, so this is exactly what we've done, and let's have a look at what that kind of pans out to. So we can take our original proof that we just walked through, and we can plug that into an egraph, and it comes out looking about what you'd expect. Now, once with this egraph in hand, we can then express optimizations in terms of transformations on proof trees. So as an example, we might come up with a rule that allows us to swap a core rule followed by a free rule, and thereby enable this kind of tail call optimization that I presented previously. Now, you may be correct in observing that this is not valid in general, but we can make sure that this transformation is sound by enforcing the constraint that the freed heaplet X does not occur in any of the heaplets that are passed into the core. And so with this, we can make sure that our transformation is sound and is a valid optimization. And the nice thing about this constraint is because of the way we've structured our proof rules, it is actually a purely syntactic check, which means that we can do this without having to simulate some kind of proof state, intermediate proof state, and can be done fairly efficiently. So taking this rule in hand, we can apply this to our egraph, and once we have an equality saturation, we obtain the following egraph. And the merged nodes represent distinct subtrees that are able to dispatch the same proof obligation. So once we have this saturated egraph, we can then perform extraction on it to extract a canonical instance of the proof, and extract also a kind of optimized program with its proof requirements. Okay, and so that works. And that's kind of the high-level idea of what we've looked into. We also looked into using sort of E-class analyses to allow expressing these transformations in a slightly more general form. And so, that's where it works. So far I've kind of shown you where it works, but a slightly more interesting question is, where does this start to fail? And really, the issues start to arise whenever you run into situations where you need proofs to start to diverge from programs, or vice versa. So I have a couple of examples of these, and I'll just quickly walk you through them in the last remaining minute. Okay, so the first one is sort of branch equivalent checking. It's a very common sort of thing that you might see in some synthesized programs, is you have a branch where both bodies of the branches are the same. And ideally, we'd like to eliminate the branch entirely. The problem arises when you try and encode this in terms of a rewrite, is that because of the presence of non-deterministic rules or context manipulating rules, you may have sequences of proof steps that generate the same programs, but are actually syntactically different. And so it's not so straightforward how we should do this kind of optimization when reasoning about directly on the proof trees rather than the programs. Okay, so another similar issue that arises is transposing through branches. So another common code smell that you can see in synthesized programs is you might have common code that occurs on both halves of a branch. And ideally, we'd like to pull out this common code outside of the condition. The problem here is that when we're reasoning about proof trees, the open rule not only simulates execution of a conditional, it also reveals certain information about the heap. And this can be problematic because it means that we may not have the information for a particular proof step to be valid prior to executing the open rule. And the final sort of issue that we ran into is, I think, the most interesting one. So this is a block of code that occurred in some real synthesized code. It's as real world as synthesized code can be. And sort of the specifics of the code isn't that important. It just occurs at the end of some code to manipulate a binary heap. And what effectively it does is it updates a binary heap to just binary tree, and it just rearranges the nodes. If you look at the sort of in-order traversal of the leaves, you can see that the order is still the same. So effectively, this is an idempotent operation in terms of the invariance on the binary tree. And so ideally, we'd like to be able to say, give the opportunity to remove this whole block of code. But it's not quite clear how we could justify this transformation because it requires rewriting or removing a whole arbitrary number of statements in the proof tree. Okay, yeah, so that kind of concludes my talk. And I'd be happy to take any questions, I guess. Well, we might not have time, but offline if you have any questions.
All right, thank you.
I'm encouraged
find speakers over lunch and ask questions, but otherwise we'll be
Yeah.
they are okay with being called back. I'm like 80% sure this person Thank you. What were the worst things that ever happened?
Yeah. Okay, so it sounds like you are.
The other thing we have to check.
And then Zach is doing what?
Yeah. I've told her the same thing. I know my laptop works.
We have.
You wanna try yours?
Sorry.
No, go ahead. No, let's hear.
So we're going to use this one for the virtual speakers. We just tested everything.
Great.
It's set up.
Whew.
We, yeah.
You got a little gather person?
We have a little gather person.
Got
it. We have the YouTube stream going.
Thanks so much for this was equally stressful. To just be here. It's just, you know, it explodes like,
hopefully this will be.
Yeah, I think so. Well, I mean, now that we know how to plug in the sound.
Yeah, yeah, we have the cables, we have the things.
I'm going to be shuffling the schedule around a little bit.
Okay.
Okay.
Do you,
I don't know.
does it matter?
Does not really matter.
Okay, yeah.
Yeah.
Yeah, I don't know if that affects us anyway.
I'm going to try to bring
So long as
Rennie
virtual
back
people know.
in.
Yeah.
I think we'll have time because I can get a no-show.
Okay.
Oh, okay.
I've never heard of such a thing, but it's actually very useful because I have to squeeze in an extra talk.
I should no-show for other stuff, you know?
Yeah, right. Yeah, open up.
No show IRL or no show virtual? What? What?
This person's paper was accepted.
Yeah.
I had never heard from them.
Oh.
They've never responded to any sort of correspondence.
Interesting.
So like in particular, they didn't check a box that said virtual in person.
I see.
That I sent them.
Yeah.
So,
yikes.
They may walk through the door at the allotted time.
I don't think that they will.
That seems exceedingly unlikely. It's possible that they're on Gather. They're not on Slack. I can't find them on Gather. So.
Also, because I'm sure
Yeah.
if you have your own implementation, it's probably.
Max, so as chairing this session, are you going to manage time, or do you want?
I'm happy to do the.
Cool.
Oh, the other thing we need to do, which hasn't been, people haven't been using this, but we started a Slack thread for every speaker.
Yeah.
You want to take care of that?
Sure.
We just haven't really gotten any remote questions.
No one's been asking there. I feel like some people have been using the Gather, or like I see sometimes there's conversations in the Gather, but no.
That's okay.
Yeah. And I guess we have to count attendance too. Which we can,
Yeah.
Is there anyone else coming?
There should be. I have been very lonely in my student volunteer.
You've been alone. With your session.
Yesterday I was alone, and this morning one of the student volunteers didn't show.
Oh, no shows.
It's in the air.
Yeah, no shows in that way. Definitely.
Yeah. Let's see. Who else is here today?
So I'm not even supposed to be here, but because of the setup issues, I think the other place is somewhat set up, and we assume that people can't or wouldn't be prepared to do YouTube here.
Yeah.
So we might have an extra person.
Okay.
Maybe I should check on that. When am I supposed to be? So I'll go check that. Either way, everything should be just going.
How hard was it to set up OBS?
It's not hard.
But you need the stream key.
The stream key, yeah. I think it's working.
All right. I think we'll go ahead and get started. Hopefully people can hear me in the Gatherverse. To kick off the session, we have Rebecca telling us about egraphs in Python. So, Rebecca, take it away.
All right. Oh, cool. Microsoft. Microphone is on. All right. So I'm Rebecca Swartz, and I will be talking today about quiche, which is an egraph library for Python, in Python, and has full dedicated support for manipulating Python ASTs, including full source-to-source rewriting. The reason that I developed Quiche, is that I wasn't quite certain that Egg would fully represent the entire Python AST, the full grammar for the Python AST. I wasn't sure about doing the translation from Python to Egg. And finally, I thought that having a native tool was actually very attractive since I intended to do Python AST rewriting. So let's go ahead and jump in with a quick example of what Quiche can do. So on the left, we have some Python source code. It's just doing a basic time conversion. You can see we've got the multiplication spelled out, and something that it might be really nice to do is to apply constant folding and get the source code rewritten with all of the constants folded. And it turns out that Quiche can do this by creating an egraph and using some rewrite rules and an e-class analysis. And I will do a quick walkthrough of the code for how we can do that in Quiche. So step one, we will parse the Python into an AST Quiche tree, which I'll talk more about later, but basically this is the input representation that we use to construct an egraph in Quiche. And the second argument that I've applied to construct the egraph there is the AST constant folding, which is our e-class analysis to do constant folding. Next, we will create some rewrite rules for doing multiplication and division rewriting. After that, and again, I'll go into some of these things in more detail, but basically we will apply the rules until the egraph is saturated. Then we can extract the smallest AST, which is the one that has all of the constants folded. And finally, our AST Quiche tree can be extracted and converted to a file. And we could, in this case, call it time folding since we were doing time conversions. So let's talk about the core implementation. These are the sort of core components that make up Quiche. We have basically the stuff that you would expect knowing what you know about egraphs. We have an egraph class, e-class analysis, rules, cost models, and extractors. But the main ones that I want to focus on most are the Quiche tree, which is the tree representation we use for building egraphs. It's also our rewriting rule representation. And also when we do term extraction, we extract back to a Quiche tree. And the other main difference that we have from Egg is when in the extractor class, where we extract terms based on the cost model, but we need some extra information because of how we construct Quiche trees. This is roughly the public interface that we have for egraph representation. Sorry? Oh, I thought I heard a question. No. Okay. This roughly, very closely follows the algorithms that are implemented in Egg and described in the Egg paper. I think the main difference here is that when we construct an egraph or when we add to the egraph, we're passing in a Quiche tree, which sort of roughly corresponds to Egg's language tree with some key differences. So let's talk a little bit more about what a Quiche tree is. This is basically a parsed tree that we use to construct an egraph. Essentially what that means is that the user is required to bring their own parser, they construct their tree, and then they can build an egraph from it. And in order to do this, they have to implement this Quiche tree interface, which provides three methods. We have a value. This is what's going to be used as the key for eNodes. We have a children, which is, this is a recursive data structure, so all of the children should be themselves Quiche trees. And finally, the big difference here is we have this is pattern symbol, which is used for e-matching. And this is our indicator for whether the node should be treated as a pattern or not. Because Quiche requires you to bring your own parser and bring a parsed implementation, we don't know what things the parser will or won't allow as pattern symbols. And in fact, the Egg syntax that they use in many of their examples for having a question mark preceded by a variable is actually not allowed by the Python parser. So that's part of the motivation for this. Okay, so continuing on with talking more about rules. A rule is just a pair of Quiche trees that we can do e-matching on. And the e-matching, so for Python ASTs, patterns are variables or strings that are prefixed with this double underscore Quiche, double underscore. And for AST Peachtree trees, which is the Peachtree implementation for Python ASTs, I've added this make rule, which handles all of the work of parsing strings into Python ASTs for you, so that that actually constructs AST Peachtrees. And this is the representation of the associativity of multiplication. So basically we have x times y times z can be reassociated to x times y times z. Cost models, these are very similar to how egg works. In fact, they actually use the same names. So I'm not going to talk too much more about those. I do want to move on to term extraction. And like we have an egg, in order to extract a term, you have to have a cost model and an e-graph and an e-class ID specifying which e-class you want to extract. But then we also have to have this build tree method, and this goes back to the fact that it's bring your own parser. So once we've gone from a teach tree to an e-graph, we also need to know how to go back the other direction to sort of construct something sensible from an e-node. And so that's what that build tree method is, and that's added as an extra parameter to the extract method. Okay, so let's talk a little bit about Python ASTs in Quiche in particular. So this is roughly the pipeline that we follow. We have a Python source file, we parse it, we lift it through a Python abstraction layer that I'll talk a little bit more about in a minute. We convert it to an AST keystree, which is an implementation of the keystree interface. We perform whatever egraph operations we want to. We construct the egraph from the keystree. And then to go back, we extract back to an AST keystree, back through PAL, and then generate the Python from there. So I'll go through this in a little bit more detail. The Python abstraction layer is an abstraction that I wrote to sort of handle the differences between different Python versions. Currently we support Python versions 3.7 through 3.10, and they all actually have subtle differences in the AST grammar. So the PAL is abstracting over those. The other reason that it exists is that we want to make sure that all of the AST nodes that go into our AST keystree actually extend the Python AST class. And when you just extract a Python AST, that's not always the case because there are allowed to be lists, and also there are allowed to be primitives. And so what this layer does is we wrap all of those, we wrap statements, expressions, etc., lists of statements, etc., in blocks, and then for the leaves, we collapse those into a simpler leaf node. Okay, so we'll talk a little bit more about the AST keystree implementation. As I said, it provides these three methods: the value, the children, and the pattern symbol. Value is roughly what you expect. Or it's just the AST node type, or we have a special tuple for leaves, and there's an example on the right side. If you look at the constant 5 example, so the constant 5 thing, that's what it looks like in the Python AST. And then underneath we have the special tuple that we use to represent the value of that. So it's tagged with its type. We have the constructor there, and then any arguments that are passed into the constructor down the line. For children, as I said, the AST keystree is recursive, so all of the children get wrapped into an AST keystree structure. So if we have an if with a test then else, all of those get wrapped. There's again an example on the right. And then finally is pattern symbol. For Python, I've decided that variable names or strings beginning with the Weber quiche notation are interpreted as pattern symbols in the code. And I already addressed why we can't use the question mark X notation like egg does. It's because the Python parser does not allow that. It's invalid syntax. And the reason that we include strings is because some things like function definitions use a string instead of a variable name for the function name. So if we wanted to be able to do function rewriting, for example, over a generic function name, we would need to be able to recognize those. So the extraction, this is just a quick summary of that again. We rebuild the AST, we extract through PAL, and generate the source code with, we actually do that with a third-party tool called Astor to generate the source code. There's a full summary of the pipeline. And just a couple of notes on things I'm looking to do moving forward with Quiche. I'm really interested in looking at new analyses and cost models. I also like to create a full suite of rewrite rules for known Python optimizations because there actually are quite a few known rewrites that you can do to make the code, to improve code performance. Kind of going along with that, I'd really like to have better project support, so where you can sort of like a one-button push, analyze a full Python project, and apply these rewrite rules and so on. And then finally, it might be nice to look at options for legacy Python systems, since there are some versions of Python that have been reached end of life, but obviously people are still using them. Up here I have a QR code and a link to my GitHub repo, and summary, and thank you.
As someone who's also implemented egraph library in Camel based on some egg, one thing that I realized very quickly after trying to implement my own was the sort of scheduling has an important role in making the thing tractable. And so a lot of heuristics I just stole directly from egg. I was just wondering, like, did you run into that? Or did you have some kind of similar realization with scheduling, or did you try?
Yeah, so the question is about scheduling and whether that's been addressed. And actually, I have not addressed that yet. That's something else that I really need to look into. Yeah. Yes.
Can I construct cyclic, I guess, code terms or something directly in the egraph?
Can you explain more how you mean?
Yeah, so sometimes we'll have operators, and their arguments will end up pointing to the same E-class of the operator. That can just happen as a consequence of normal rewrites. But sometimes the term I want to represent itself starts off cyclic. I was wondering if there's any challenge there with the sort of bring your own parser, and we can also, I can show you an example offline too.
All right. Yeah. The question was about cyclic terms and representing those, writing those immediately. And I would really like to see an example of that offline. That would be great. Yeah.
One big challenge for optimizing imperative programming languages like Python and egraph is all the statements.
Right.
Is quiche limited to the expression level, or can you write patterns across statements?
No, so you actually can write patterns. The question, Sarah, was whether you're limited to expressions or if you can write patterns over statements. You can, in fact, write patterns across statements. Well, you can certainly do at least one statement. You should be able to do more than one. Yeah, you can.
Along similar notes, what do you do for loops, like for loops or other kinds of loops? Do you support them on that? If the Python program has loops in it?
Yes. If the Python program has loops in it, do we support that? It's just represented as an AST.
Right.
And so, yes, we can capture that in the AST.
Let's take a speaker here. Alright, so the next speaker will be Remy. We'll be trying this once again, but we think we have the AV issues sorted, so everyone buckle up. Cross your fingers.
Oh no.
Rebecca, can you please step off the virtual stage?
Okay. How does that sound?
We can hear you.
Ready? All right. So it sounds like there's feedback, so I'm not gonna ask. I'm not gonna raise it to the audience. And let's try to share screen. Looks like it's working. Let me know if there are problems. Yeah, I mean, I just really want to thank Matt for putting this out. I'm really sorry for all the issues. So hopefully this is working. So it turns out I had too much distortion on my guitar, and now we have a unplugged version of my microphone. Okay, so I'm going to talk about the automata. This is kind of a recap of what we had in the morning. So now that I'm talking about some CTA, CSM stuff. Okay, good. hear more about the topic. So since I cannot hear you, this quiz is not take home, and then I'm gonna tell you the answer right away, so you can do the example myself. Right. So the question here is that we have these terms. We have the x variables, and we have the y variables, and then we have these applications applied to x's and y. And the question asks, what does the E-graph look like if we insert all units into the E-graph? Right. So it's a bit of a trick question because the E-graph is really important, and then the reason is that we have not asserted any equivalences. So everybody is in its own class, right? It's not interesting at all. So let's spice things up a little bit, and then assert all the x's are equivalent, and all the y's are also equivalent. Right. So now to reflect these equivalences in the graph, we're gonna merge the classes of the x's and the classes of the y's, and there's more. So now that these are all in the same E class, we see that these four f's are now what is called congruent. So we're going to merge all of the f's into the same class and deduplicate. Right. So this is a classic observation that congruence can sometimes compact the equivalence. So let's take a step back and then think about a different scenario. Right. So we asserted these variables to be equivalent. So now let's take that away, and then instead we see that the F applications are equal instead. Right. So in the E-graph, this looks like this. So we're only going to merge the F applications together, and that's pretty much it. Right. So we don't have any congruence. So we don't have congruence anymore. So now with this equivalence, we can get really any compression, any additional compression. Right. So there are certain circumstances we would like to compress the graph even more, and we're able to compress it even more. And then for that reason, so I'm going to tell you that the f function is actually this predicate that tests if the input number is even or not. And the variables are actually numbers, so we have these odd numbers and we have these even numbers down here. Right. And then suppose that we are only able to observe the output of this even predicate. Then given that, all of the odd numbers will actually be, in a sense, observationally equivalent. So we cannot distinguish between the odd numbers if we only can only observe the output of it's gonna output false for all of the odd numbers. And similarly, we cannot distinguish between the even numbers if we can only see that the even returns true as a result. Right. So this is in a sense a version of observational equivalence, which is kind of a dual to congruence. It's effectively a co-congruence. Right. So using this observational equivalence, we might want to merge and deploy this even application, given that this can be merged under observational equivalence. And then that's exactly the goal of the remainder of my talk, which is can we take advantage of observational equivalence in E-graph and achieve further compression. So let's go back to this stage before the merge, and then try to go from down here. And just like every single problem in computer science, we solve the problem by writing regular expression. Okay. So this part is going to be a little magical and maybe a little confusing, so bear with me for the moment. So it might be unclear for you. Okay. So the first step is that we want to turn all of these terms into strings. We're turning into strings in a bottom-up manner. So even 1 becomes 1e, even 2 is not here, even 3 becomes 3e. Right. So this is not always possible in general, but right now we just consider the cases we can turn into strings. And now we're going to write down the regular expression that corresponds into the yellow classes. So one way to do that is that we simply put a disjunction among the 4 expressions, right? So we choose 1e, 3e, 5e, or 7. So this corresponds to the E-graph in the bottom. Another way to write this we kind of push down the assumption, and then first make a choice between 1, 3, 5, 7, and then we say that this choice is followed by the even. And next, we're going to write down the finite state automata corresponding to these rubber expressions. Right? Yeah, and just to kind of brush up on some automata theory, this will be what they look like. So here we have transitions from the start state, and then over here we have intermediate states. So here, we see a character 1 will go to this state, and we see a character E will go to the second state. And then this automata corresponds to the second expression. We see any of 1, 3, 5, 7 will go to this state. We see E again will go to the second state. Right? So in reality, we can actually transform this larger automaton into a smaller one. So this is pretty well studied, and then most record expression library will implement this procedure. It's called a minimization of finite state automaton. Right, so this will become important later. And now this is where the magic happens. Right. So by doing some transformations, we can actually take this automaton into an E-graph. And we're going to start by pushing all of these transition labels into the space. Right. So E is going to go here. Number is going to go into this space. Right. So ready? Yeah. And then next, we're going to flip the arrow to point from the transition into the state set. Right, so you look at this arrow, I'm going to flip it down in this way. And then finally, I'm going to just drop all of the arrows at the mid position, and that goes from start state. Right. So at this point, you see that what we have here is exactly the same as our goal automata, and then we can read off as it. So going up level, we can do this because there's this really beautiful correspondence between E-graph and then what is called a deterministic finite state tree automata. So tree automata is a generalization of string automata that works on trees. Right. So the way it works is that an E-class represents a set of terms. So each E-class is mapped to a state that accepts a set of terms. And E1 connects its class, the class it's in, with its children classes. And this corresponds to a transition that goes the other direction. Right? It connects input space to output space. So this is why we need to split the arrow. Right? And then we have some root classes or root classes in the E-graph we care about. Usually we just extract our final expression from the root class in the graph. And this corresponds to the final state or final states that accepts the terms. In the tree. So this is super cool, but why bother going through this route? Right? So one of the reasons that we might care about this is that we know how to minimize deterministic finite state automatas. So this was the minimization procedure I showed you earlier. And then this essentially leads to a way to also minimize E-graphs. Right? So what we can do is that we first translate the E-graph into a tree automaton, as I showed you before, and then we're going to minimize the automaton into a smaller one, which we can translate back into a smaller E-graph. Right? And then this essential step of minimization essentially works by merging classes that are observationally equivalent. So in terms of practical application, we apply this minimization technique to shrink the E-graph before we use an LP solver to do extraction. So here you can look at this data point, which basically says that after minimization, the ILP runs almost 100 times faster than before. Right, so this can speed up lots of the graphical things. And then in terms of theory, there has been a lot of study on, or there has been some study on a notion of completion. So think about Knut-Dennis completion for tree automata. So it, in a sense, essentially corresponds to adding rewrite rules to the E-graph. And then we can using this, we can approximate a tree automaton completion by adding some edits to the points over the graph. And this means that we can prove some Irish results, which is pretty powerful. Okay. Yeah, so if you want to take away one slide from my talk, this is it. So, essentially this is the Rosetta Stone tested in between graph and Turing. Okay, I don't hear anything for.
Hey, Remy, can you hear me?
No, I don't think you can. I don't have the microphone in this one.
Go in the orange box.
Yeah, should I get up or are there questions?
Hey, can you hear me? Hello?
Yeah.
Remy, can you hear me?
Yeah.
Great, all right. Great talk, Remy. There was applause, so much of it. I kind of needed it because it was overwhelming. Any questions for Remy? I will relay them to you.
What's the complexity of BFT analysis?
Yeah, so one question for you, Remy, is can you say anything about the complexity of VFTA minimization?
Yeah, that's a wonderful question. So what I implemented was pretty slow, so I think it was like quadratic or something. So I think there is no algorithm that has n-log complexity, which I think is the same as minimizing string automated, which is still not that great. It's not it's not constant. So we can't really afford to run it too much. So in the application, we only run it once right before extraction.
N is the number of nodes.
Is n the number of nodes there?
N is the number of either states or transitions, so I have to go back and check on that. Yeah. So states correspond to classes and transitions correspond to nodes.
One question from the chat is from Sam Howard. He says, can you say anything about this being implemented in EGG or another eGraph framework? What would the user need to supply to implement this? Remy, you muted yourself there.
Yeah, thanks for the question. So we would love to see this implemented in EGG. And I actually forgot to ask. So we are looking for collaborators because now I have more time to work on this. So if you're interested in implementing this, shoot me an email, shoot me a Slack. We'd love to collaborate. So the user, to use this, the user shouldn't be able to, input anything extra. So this is, fully, I think it is a further switch.
Great. All right. Let's thank Remy again, and we'll have the rest of the Okay. So the next two speakers in this session are also remote. All right. I think you're already ready to go. So you want to go ahead and share your screen and take it away?
Hi, thanks, Max. Okay, hi everyone. My name is Ajay Rustan. I'm a PhD candidate at Cornell University. Today I'm delighted to present our work on generating optimized large integer multipliers on field programmable data arrays using egress and equal saturation. Our work impressed is recently published at the XCCM conference. With the ever-increasing security requirements, novel cryptographic algorithms are being proposed and the complexity of the existing algorithms are being increased. Fully homomorphic encryption allows third-party computations to be performed on the encrypted data. Integer-based FHE algorithms rely on very large integer arithmetic and multiplication in particular. Similarly, for RSA, key size requirements are constantly increasing. Typical sizes today are 1,000 and 2,000 bits, but the recommended size for the near future is already beyond 3,000 bits. Such applications with high arithmetic intensity need to be accelerated using special hardware. Here we see a spectrum of compute devices. On one end, we have CPUs which offer high flexibility, but they lack energy efficiency. On the other end, we have custom ASIC giving the highest efficiency, but it is also the
which are tailored to a specific domain of applications such as the convolutional neural networks. And FPGAs, which are field programmable gate arrays, offer both high performance and energy efficiency. These are reconfigurable devices, meaning that you can reprogram them to implement any application. The majority of the cryptographic accelerators in literature use FPGAs. An FPGA is inherently parallel with an array of logic blocks, interconnects, IOs, each of them being programmable, and also some dedicated blocks. A key input lookup table, also called a LOT, can be programmed to implement any k input one output function. So for instance, an adder can be implemented with a network of lookup tables. There are typically around 1 million lookup tables on the FPGA device. There are also hardened digital signal processing blocks on modern FPGAs called DSP, which are essential for high performance arithmetic. Multiplications and additions of a certain size can be mapped to a DSP block. DSP blocks are highly configurable, and there are typically thousands of DSPs on the device. FPGA design can start with a high-level specification, such as a behavioral description in C++. Then high-level synthesis, or HLS, translates this description into a hardware description language, such as Verilog. And then downstream synthesis starts, which consists of logic synthesis, placement, and routing stages. Placement and routing is the most time-consuming part of the whole design flow. It can take hours to implement a mid-scale design, and that's why HLS offers a faster hardware development. But it's hard to rely on HLS compilers in our case because they do not handle large integer multiplication very well. HLS generated 256-bit multiplier operates at a very low frequency, 18 megahertz, and it goes down to 5 megahertz at 512 bits. And larger multipliers can even be synthesized into resource overutilization. Multiplication is typically optimized with decomposition methods. The expression tree on the left corresponds to the school book decomposition, where each operand is split into two parts and we sum up the weighted partial products. And another method is Karatsuba, which uses a trick to reduce the number of partial products from 4 to 3. And of course, this introduces more addition and subtraction operations. This trade-off between operations is reflected in the utilization of different resource types on the FPGA. The table lists the DSP and utilization of different approaches across different multiplier sizes. Karatsuba gives minimum DSP, but the significance of its box overhead depends on the multiplication size. So the overall resource trade-offs are non-trivial because there will be multiple levels of decomposition and different choices exist at each level. So let's try to illustrate that. We start decomposing the embedded multiplier with either method, then we further decompose its partial product, and this can go on. And do we know how deep the decomposition should be, or do we know which method should be applied at which level? It's really hard to know because of the heterogeneous nature of FPGAs, where the trade-offs between different resource types are non-trivial. And to give a very simple but concrete example, here we list 3 different ways of rewriting a 256-bit multiplication with up to 1 level of decomposition. These implementations are fairly optimal because among these solutions, DSPs cannot be reduced without consuming more loss. And if we consider another level of decomposition, with 2 levels, there are actually 27 different ways we can rewrite the multiplication, but here we are listing only a few. Now we see that although schoolbook was pretty optimal at the first level, when it's followed by Karatsuba, it yields a non-pretty optimal design point because it is now dominated by the 1-level Karatsuba implementation. And this reminded us of the frequently encountered problem in compiler optimization, which is the phase ordering problem. Basically, locally optimal decision may lead to a globally suboptimal result when followed by other decisions or vice versa. Cryptographic algorithms include very large integer arithmetic, and we don't have the libraries and compiler support to efficiently implement them in today's compute devices. And our goal is to devise a framework which will find the optimal HLS C++ implementation for the integer multiplication problem. And when it's synthesized, placed and route on the FPGA, the final implementation will meet the application requirements on the resource types. And in a nutshell, our framework defines the source space with equality saturation, extracts optimal expressions using an exact ILP formulation, which also supports multiple objectives, and does code generation to convert the optimal expression into C++ for HLS. To prevent the payload problem, we are using equality saturation, which lays out the complete design space Here I'm showing our rewrite rules. I don't have much time to explain these in detail, but basically they cover school book and curricular decompositions, different DSP tiling patterns of small multiplier units, and a few other transformations which are explained in more detail in our paper. But please note that we define bit-accurate operators and transitions because, for instance, the hardware cost of a 32-bit operator is different from the cost of a 64-bit operator. And also, the same decomposition rule does have different impacts depending on the multiplication size. So we use egg as our equality saturation engine. The final E-graph after equality saturation contains all possible ways to rewrite or implement the given integer multiplication. This figure is a very tiny example. It is a saturated E-graph corresponding to 32-bit multiplication using only 3 rules given in the slide. And here's our scalability analysis for increasing multiplication sizes. With only hundreds of nodes, our E-graph already represents millions of expressions, and the growth in the E-graph size is significantly slower than the growth in the number of expressions. And equality saturation runtime is on the order of seconds. This scalability stems from the comments of expressions within and across our custom rewrite rules. The current one showing entire rule sharing. And if we go back to our previous time saturated example, highlighted are the roots of the shared sub-expressions, both within and across rules. Once we have a saturated E-graph, the next step is extracting the optimal expression based on a cost function. Yesterday, Max mentioned X built-in bottom-up heuristic, which supports a single objective. We devised an ILP formulation which allowed us to perform optimization with multiple objectives. Our tool supports both DSP constraint block minimization and also DSP block co-minimization. I put the formulation here for reference, but unfortunately I won't have time to go over it. Once an expression is extracted, our tool translates that into C++ code for HLS. Here we leverage subgraph isomorphism. Basically, rewrite patterns are matched with subgraphs in the expression graph, and then the corresponding C++ functions are automatically instantiated. Back to our scalability analysis. In terms of extraction runtime, X heuristic is comparable to our ILP extractor until 512 bits. And then ILP starts to take significantly longer due to the significant increase in the number of ILP variables and constraints. But although it will take longer, it's generating lower cost expressions as shown in this new table. And this is due to the underlying assumptions in the heuristic, again, as mentioned by Max yesterday. To measure period optimality, we exhaustively collected and implemented all the expressions corresponding to a 64-bit multiplication. The expressions found by our tool are marked in magenta. 12 out of 14 of these expressions are on the actual Pareto frontier, and the 2 non-optimal ones have only 2% higher lot utilization compared to the optimal ones. And the result of the default HLS implementation, the baseline Karatsuba results, and also the single objective extraction are also marked on the same plot. And to illustrate the flexibility of our tool in controlling the DSP utilization, we also show the results for the 256-bit multiplication on the right. Now let's scale up to larger multipliers. We have a million-bit multiplication used in integer-based FHE applications. We first apply number theoretic transform to break the million-bit multiplier into 1024-bit multipliers, but still the default HLS implementation leads to a placement failure on the device. With the baseline Karatsuba approaches, we can fit 3 instances of this complex design on the FPGA device. This number cannot be increased to 4 because of either DSP overutilization or lot overutilization. But with the flexibility of our tool in controlling DSP versus lot utilization, we were able to fit 4 instances instead. In conclusion, we propose an integer multiplication rewriting framework for FPGA HLS. We define and efficiently explore their rich design space, and our framework provides high flexibility across multiple objectives as a result of the ILP formulation, which needs improvement in terms of scalability, but that's for future work. Our paper is available online. Please check it out. I'm looking forward to any questions or feedback that you have. Thank you.
Sorry. Thanks for the great talk. Do we have any questions from the audience? Because otherwise I would have some questions. I would like that. I'm always too scared to type FPGAs, so I'm glad. A question from the back is asking, are you aware of the other work in equality saturation that has used ILT-based extraction? Because it seems like that is a bottleneck in your framework. Like, did you have to do anything like cycle pruning or anything to improve the ILT scalability of your algorithm?
Not really. Actually, we don't have any cycles in our e-graphs, first of all. And since we are operating on bit accurate operators, when we apply our rewrite rules, the e-graph doesn't explode at all. But definitely we need some sort of tuning for future studies because we cannot scale very well beyond 2048 bit multiply, if that answers the question.
Yeah, no, that's great. That's great.
Thank you.
Are there any examples you found where the graph didn't saturate? Because I thought most of the examples you showed the graph did saturate, right?
Yeah, so the question here is about the saturation of e-graphs. The example you gave, the e-graph actually saturated. In practice, does it always saturate, or what frequency of the time does it saturate?
Well, in all of our multiply examples, it's saturated all the time because I think with the help of Max, we defined an unlimited time limit in the React framework, so the tool waited until it's fully saturated. That's what we asked the tool to do.
Cool, so I have a follow-up question to that. This seems to be one of the rare domains where equality saturation kind of just works without any tweaking. In my experience, you got to do some kind of pruning, or you bring in an analysis to do something clever, and we've had a couple talks on that earlier in the day. Do you think that, I don't know, what is special about this domain that it seems to work so well, or do you anticipate that you'll have to start using some of these techniques to, I don't know, to scale to larger problem sizes?
Yeah, so we definitely need to scale to larger sizes because, as I mentioned, certain applications need million multiplier, and we have to use the number theoretic transform to break it down. So what if we didn't have to use the NCC and directly use our tool to optimize the million multiplier? That would be a really cool direction. But at the moment, since we have a limited set of rewrite rules, we didn't need pruning up until 2000 bits. But beyond that, we would definitely need that, and a potential direction is that where there are so many expressions with the same hardware cost, if we were able to detect that and prune accordingly, that would be a cool direction.
All right, let's thank the speaker again for a great talk. All righty, the next talk will be by Javier telling us about WASM, egraphs, and mutants. He's heading to the stage.
Hello, can you hear me?
Yes, we can hear you, Javier. And we can see your screen, so take it away when you're ready.
Oh, okay, perfect. Yes. Can you see my screen?
Yes, we can see your screen.
Okay, perfect. So, hello everyone, good afternoon, or good morning for me. It's almost midnight here in Lisbon. So, my name is Javier Solera. I'm a PhD student of the BTH for Institute of Technology. And thank you for being here listening to the last work, to recent work of the WASM debate. So, yeah, so I will be talking about how or using a strategy or using a strategy for WASM compilers uses EWAP to reach, let's say, the requirement that the previous user using a study. So before going into the details, I would like to start using a little bit the language that we are talking about. So yeah, WebAssembly is acknowledged as the fourth programming language for the web browsers, along with HTML and CSS. JavaScript, and it's just basically allows you to execute bytecode on the browser side. in a faster way. To say it's safer and faster than the standard version of code. Yeah, and beyond the web browsers, it's also evolved to be executed outside web browsers, specifically for some CDN architectures or services offer their platforms to execute directly WebAssembly code in the backend, not precisely in the web browser. For example, Cloudflare or Fast use this on a daily basis. And yeah, WebAssembly it's still not completely secure, and even though the specification of the language is super clear and so on. So these three works are basically the state of the art or the most remarkable works on the state of the art for WebAssembly. And one interesting fact here is that WebAssembly lacks a couple of benchmarks beyond the specifications. So for example, it's true that you can check and you can create your test based on these specifications, but still the compilers and engines fail to some super weird cases. So the question here is how to find these cases. And here is when the automatic testing pays up, and specifically fuzzy. So yeah, what is fuzzing? The main idea of fuzzers is to generate random inputs, checking for patches, right? So you generate a random file stream and then you pass it to this program and then you try to match patches first. For compilers, this is quite dummy, since it may be we may be generating a statically correct program maybe in past years to use just few random patches. So fuzzing for compilers is usually achieved by using grammars, right? I mean, if you create a grammar for your program, you at least can ensure that the programs that you generate randomly are syntactically correct. But okay, so you can be smart in this way. If you create a grammar and you can be fast, you can get syntactically correct programs really fast. However, what happens with these programs? I mean, once you reach the semantic stage, then you have to take programs like these programs that you generate as syntactically correct phase in later stages. So what to do here? So there should be a way to traverse all the semantically equivalent programs space. So once you traverse this semantic checking and then the compilers, for example, generate some matching code, you should be able to get this program that reach this super latest stage and transform it somewhere in a way that even though this, you can generate a semantically equivalent program, reaching deeper stages. And here is where our tool came up. So what's innovative in this context? What it does is to take an pre-existing WebAssembly binary that's perfectly valid and it passes all your engine by default. And it explores the spaces of all programs that are semantically equivalent to the input of the binary. How it does it? So it applies code transformation to the programs in order to generate program files. And here is where the core of our tool came. So we were finding a way to apply this code transformation in an efficient way and not applying all one behind the other randomly. And then we found the Egg project. So we found the eGraph and we found the super cool project. And when we read this image, the description of this image, something really came up, and this was this specific play. So if you take the eGraph, any eGraph, so in theory, whatever byte you get in the path in the eGraph is semantically equivalent. So this means that you can construct a big eGraph from an instruction in a WebAssembly program or whatever program, and you can write several semantically equivalent targets. If you write, I don't know, maybe hundreds of rewriting tools that make sense for you. Then the key insight here is to traverse the eGraph to generate the semantically equivalent programs in another way. So why other ways in codes here? that we saw is that as for example, if you use the egraph, you traverse the egraph, and you get a semantically equivalent program of the initial one, and if the launches a crash in the engine, so by default, if you do this traversing in a order way, this means that, for example, you can generate small programs in a certain order in terms of size. So by default, you will get a best use case. Yeah, so Watson mutate, just to recall a little bit, so Watson mutate selects a random distribution with the binary code of the input program. It builds the data flow graph from the instruction, it creates the egraph, and it traverses the egraph a really large number of times, creating n programs. So this is the algorithm for the traversal of the egraph. So basically, we take the egraph, we take the egraph for the one that we want to start, we idle the instruction of this force, and we set the maximum length of the egraph traversal. So here the E is in line 6. So the first branch of the comparison, of course, if the gas is or the fuel of this traversal is 0, then we most smallest. If not, for the class that we are, we select a random node, and from this random node we traverse its operands, and we conclude this way random traversal of the egraph. So how can we, in fact, test that this is doing something useful? So, okay, so we took Watson Smith. Watson Smith, as I mentioned before, is a grammar-based tool to generate syntactically and valid programs. And then these programs, in this first experiment, we passed it to Watson parse to generate the matching code out of it, and we get the coverage code. And a second experiment was to, okay, let's say Watson Smith, let's create a perfect valid Watson file. Let's pass it to Watson mutate. Let's generate several equivalent variants, and let's pass to Watson parse again, and then let's get the coverage. When we did this, we got these results. So as you can see in the first stages of the Fusion campaign, we can see an increase on the coverage number of lines, even with the same input generated to Watson Smith. We were able to pass, as I mentioned before, the latest stage of the Watson parse, and somehow using semantically equivalent programs we reach even deeper code in the Watson parser model. In the end, we were able to manage to get more line coverage over time. So what you see in orange is using the Watson mutate pipelining, and in blue is the original use on Watson Smith. So Watson mutate. So we also changed it. Synthetically speaking, we changed what habitual boundaries are going to be. For example, what means semantical equivalent? Semantically, in practice, is a super relaxed concept. But for example, we can write this directly in our Watson mutate. And using the project, we can say, okay, everything constant that you find, just create a variant that adds one to it. So in theory, this is not semantically equivalent as
guess we'll give him a minute or two and ask him something. He's so close to the end. Zach's frantically.
So Phil and I are playing tag.
You seem to be going faster on downtown.
Tag.
Better, can you hear us?
We haven't changed anything on our side, so if he's speaking, like, we would hear it.
Yeah. Okay, I thought you can hear us.
I mean, I don't think we can hear.
Yeah, we cannot hear now. But we haven't changed our sound, so I think this is on the Zoom. I mean, I think there may be a sound problem on your end. You just can't hear it. We heard almost the whole presentation. We were on the very at the very end.
And
We can hear you now.
okay. Okay, so yeah, I can share this screen again if you want, but
I think we are basically at time, but I'm glad to have you back, so maybe we can take a couple questions. Does that sound good?
yes, yes.
All right. Do we have any questions? Otherwise we can-
How do you get the rewrite tools for doing the equivalence?
Yeah, so this question is, where do you get the rewrites that you use to build the eGraph? Is there some sort of, how do you know what the WASM equivalences are?
So yeah, so we did this by hand. So we do the most traditional management. Explain reduction operations and, for example, constant folding as well. But maybe when we start like playing it and say, okay, we get something maybe not necessarily optimal, and then we start writing like these for operations and these operators and function writing.
Cool, and I've got one question. Did you find any bugs? Did this include the
That's a good question. That's a good question. So, in my defense, this is work in progress. And the other thing with boosters is sometimes you get the result in 2 hours, sometimes you get the result in 6 hours. So sadly, we haven't found any books yet.
All right, well, I covered a promising metric then. We are at 3 o'clock, so I think we should cut off
I downloaded Chrome for the sole purpose of using down there.
Okay. I mean, I could load up Chrome on here if you want. What's it like? Shouldn't it be displaying?
The speakers is sharing screen.
I mean, no. Sorry, I'm plugged in.
Oh, is it off?
Oh, she's off. Your drinker's just off.
You have to stand up there, turn your laptop around, and hold it up so we can see it.
Don't even start. Is it warming up? Oh, the old lens cap problem. The speaker is trying to me out, and I want to do it in front of me. Well, then you were the only one with the power stop, and you did, so.
My microphone's on, so I guess.
You're not. No more shares, okay?
And I guess ostensibly this could be right. With the speaker trying saying something, so we just have the audio. That's me, right? So let's try again.
Yeah, once more.
Cool. Great. So now.
All right, folks. Let's resume the final session.
Then the next one.
Oh, okay. All right, let's get the session started. The next talk is about finding equivalent structure in current programs.
So everybody sit.
Take it away. We can hear you. We can see you. You're good to go.
I cannot hear it.
We can hear and see you. You're ready to go. Take it away.
Okay, thanks. So, hi everyone. I'm Henry from research engineer from PLDI. Today I will be presenting our work on optimization of equivalent concurrent computations developed for zero-knowledge proof systems for Java program. And actually, since the presentation on zero-knowledge proofs was a bit hard to grasp in a short time, and thanks to discussion with Matt, I have updated it all to present the problem in more general and hopefully more understandable setting of formulas. The goal will be to optimize the common sub-expressions in them. Also, since it is half past midnight here in Europe, and my focus is a bit loose, I will let you watch the pre-recorded presentation of more concept from this afternoon. Feel free to ask the questions in the chat during the talk. It worked like 2 seconds ago. I will stop sharing and I will try to restart the presentation. Give me a minute. So, one more time.
Jennifer, I don't think we're getting audio from this presentation.
Oh. Okay.
In my experience, capture doesn't have audio works exactly when you don't want it to. It seems to be more intensive.
Still no audio.
Still good? Okay, so I will try to present it.
Okay, we'll do it live.
Yeah. So, I'm prepared for that. Let's do it. Give me a sec. So the problem we're going to solve is how to find the common sub-expressions in the independent from the arguments and factor them out into a separate function. So basically the problem of refactoring. So we have some expression P and we would like to replace it by function G on all its occurrences. And the thing will be that we want to either replace all the occurrences or none. To give some concrete example, we have two variables that where we have some initialization of multiplication in one variable, and in the other variable using a semantically similar initialization with bit shift to the left. And we would like to extract this pattern of initialization to some separate function. Where we can use this kind of applications, surely it's in program refactoring or in term simplification, and in our case it will be in the circuits of course zero-line tools, where we would like to extract some arithmetical logic units for multiplications and other heavy operations like divisions. So the programs we need to solve are to keep the equilibrium saturation algorithm as it is and add only some small changes to it. So we will need to extend the image algorithm to find multiple common sub-expressions and then represent the old match sub-expressions in some way like egraph so we can replace all them together. And finally, extract the refactored structure. So we will now go these steps one by one. First thing we can apply to generate right rules as in general equality saturation. Here we have the formula from the previous example where we can replace the bit shift left with the multiplication from 2, and we can see see that in the pulse we have both forms, so now we can better match on the same pattern in the both initializations. So to match both initializations, we extend the language of rewritables by a so-called variable or eager pattern match, eager matches, where we can match all of patterns that corresponds to our pattern in here the 2 times multiplication value. So in the end, we will gather all these expressions in this collection of the patterns. Next, when we have this collection, we would like to somehow relate them together so we can replace all of them or none of them at the same time. To do so, we extend the graph by so-called point nodes, or in short, E nodes, and they really represent the relation between multiple E classes, so they can be replaced all at once or not. These E classes, these point nodes keep the relations between parents and children, so that when we are lowering them in the next step, we can retrieve back to the original structure if we don't replace all of bonded nodes. So we can see here, if we bond both multiplications and we say that this bond is equal to some function called g, we can either pick the origin of the multiplications or replace them by the function called the g function. You can see that this does not actually represent the refactoring that we wanted to achieve, that is, the multiplication, that is, that the g function call should take the arguments of the actual multiplications, but it does not happen in this case. So, to do our goal, we extend the bonding also with a parameter where we can say, let's bond these two E classes, and if we wanted to replace them in the final solution, replace them with the parameter. So then, when we are extracting the final solution, we can either pick both multiplication E classes or replace them with a function called G. To put everything together in this horrible example in the end, what we have one pattern where we first match on all the expressions of a given form, and we keep variables denoted with the question marks in yellow for the later use on the right hand side of the rewrite pattern. The right hand side of the rewrite pattern then generates G structure, which is the red part on the right. This is the actual refactored function called outside of our structure, and also it creates the bonding structure inside of our E graph that represents that we can replace these two patterns with our refactor structure. Having this kind of E graph, we can then use the usual E graph algorithm to at the end extract the solution. We have developed this algorithm to optimize the circuits in the zero-node group, where we have tried by some rules to extract the multiplication of divisions, and you can see in this table that this algorithm was able to reduce almost all multiplications to a reasonable amount, and given the reduced amount of multiplications in arithmetic circuit, we are generating the logic gate circuit, which is smaller in about 20 to 25% to the original size. We didn't optimize all the multiplications because some of them had dependencies in the circuit, so we cannot get rid of all of them to a single multiplication. to sum it up, the implementation was inspired by egg algorithm, and we have extended it in our C++ library that will be soon released in this GitHub repository, where we provide our new extended language, pattern rewrite language, where there is bonding and various patches, and we use this for the zero-knowledge circuit to circuits. Thank you for your attention.
All right, thanks for the talk. Do we have any questions from the audience? I have a question. In your examples, the B node creation, the bonding procedure, you only have it only goes one deep. Like you bond together two multiplications. Does this compose? Can you recognize common substructure deeper than a single node?
Yes, you can. You mean like in this example we are already matching on a deeper substructure. If you have two multiplications nested, you can see that there is the pattern has two multiplications, and the pattern is actually this whole structure in the. Is this the question?
I think so, yeah. I think that answers my question. Great. Thanks. All right, let's thank the speaker one more time. All right, the next speaker is Sam Coward, and he's going to be telling us how to put all of abstract interpretation, all of it, into the eGraph.
Cool. So I'm actually really shocked that I've been the first one to make this joke. Clearly, I can put my affiliations within an eGraph, so I'm a child of both Imperial and of Intel, and of course my supervisor George, equivalent to Imperial, and Theo, who's in the room, is of course equivalent to Intel. So what we actually be talking about today is about how do we actually abstract interpretation of eGraphs. For those that were in the tutorial, apologies, we are going to cover some of the ground that Matt went over yesterday, but there will actually be some nice lemons stated and things like that, and Matt maybe apply some of the important stuff just a bit haphazardly without really justifying why I'm doing it.
Never.
So of course I do wear my mathematician hat as well. So brief definitions. Abstract interpretation is all about lattices, so these partial order sets, and the key thing is we have these B-star bounds, which are called joins in my notation. Maybe some conflicts here on the notation, I'm afraid, as well. But the key one that I'm going to be interested in is this greatest lower bound, which I call a beat. And so in bounded intervals, this is our intersection operator. And so basically what all of abstract interpretation is all about is taking some sort of concrete domain. So we've got on the left this C lattice that might be some properties such as what are all the possible outputs of our program, what are all the possible execution traces, all that sort of stuff. And then we might have an abstract domain where, via some hideous Galois connection, if we really want to go into the juice, you take some concrete properties and you use this abstraction function to project them into the abstract domain. And similarly, we can take our abstract domain elements and project them back into our concrete domain. And obviously, you lose some precision as you go in each of these directions. But what we're going to do is we're going to abstract some concrete properties into this abstract domain. And why might you want to do this? Because it's actually a lot cheaper to figure out things in this abstract domain. So the key things that all of our work is going to be based on is these two key levers down below. So basically, sound abstraction means just that it's okay, it's fine. It actually is correct. And so,
could you unmute yourself on gallery?
No, hope you everyone can hear me now. Sorry. So this first limit just basically says that if I have some sound abstraction of one expression and I have another equivalent expression, then the sound abstraction of the first one is still a sound abstraction of the second one. And that's basically saying that I can use a single abstract element within an E-class, and it works for all possible nodes within that E-class. Prove that, but not here. I don't want to go into that. But this is the sort of thing that you can haphazardly, as soon as you break equivalence, you introduce a rubbish rewrite rule, this won't apply anymore. And so similarly, we have our potentially two sound abstractions of an expression, and we actually know that the meat of these two things is a sound abstraction of this expression. So basically, integral arithmetic stuff is going to look at how do we abstract real arithmetic expressions with intervals. So I think for everyone who saw this yesterday, we're going to look at x minus x is a really rubbish example where integral arithmetic fails because you basically discard any correlation information in order to compute things really cheaply. So you get this rubbish, but of course E-graph rewriting gives us this, and we obviously know that 0 lies in a degenerate interval, which is just 0, 0. So we can take the meat of these things, and of course, because we have all these nice properties of lattices, and we have equivalence, and all the lemmas this relies on before, we know that this is actually a correct abstraction of x minus x. So how do we actually combine these things? We can actually use a C-class analysis and attach some abstract elements. But we work our way upwards, because of course we know we can insert properties about our constants and our variables, and then we just propagate these up through the E-graph, like we saw yesterday. We just propagate these intervals using the abstractions of what these plus node might mean in the interval domain. But of course, this can be much more complicated. In different abstract domains, you might abstract nodes like plus in different ways. And then we can apply rewrite, and of course, we get our top equivalence class might contain a couple of different equivalent expressions, and we take the meat of these two things, and we get this nice, in this example, we know the right hand interval dominates the left hand interval, so it just obliterates it. But of course, this might be a subgraph of a much bigger E-graph, and so we'll then need to propagate this information upwards. So this is where this backward arrow comes back in here, because of course, based on the information we learned from the meat, we may need to then update a load of parents. Maybe we've learned a load of new properties that we can propagate back up. And so this is something, so it's been really interesting today. There hasn't actually been that much talk about rewrites, which has been surprising to me. And this is basically all my work relies on conditional rewrites. We'll talk at the end about what my work is more focused on. But basically we say, if some condition 5 holds, then we say that the left-hand side is equivalent to the right-hand side. The obvious example of this is, if 0 is not in some abstract element, so this crazy square bracket notation around A just means what is the abstract element associated with A that we have at the moment. So what is the interval that A lies in that we understand. And so here we have A over B can be region of 1 over B over A. And this can be really cool, because what if it's not just A that we have? What if it's not just a single variable? What if it's something more complicated like x plus y? And I actually want to divide through this because this actually obliterates the dependency problem by doing this rewrite. We can only do that because we've learned that x plus y doesn't contain 0 in its abstract interval. We've learned that this is a safe rewrite to apply. So this is cool, but what does it actually mean? It actually means you get into this really cool virtuous circle. You get some information, you learn some properties, so you do your naive abstract interpretation, you push it all the way up, and you learn properties. Then you might be able to apply some conditional rewrites. That's cool, you add new nodes to your E-graph. Oh, but what have you done then? You've added new nodes, maybe you've learned some additional properties. You've got rid of some dependency problems in one part of the graph. All this stuff is great. So you've learned new properties, but maybe that enables further conditional rewrites, and so on and so forth. You can keep going around this loop as many times as you want. So it's all about learning properties and applying new rewrites. And there's a real bonus. This is kind of fun. So another topic that has been sort of alluded to several times, and hasn't really been fleshed out about cyclic E-graphs. So cyclic E-graphs is something that pretty much, I think anyone who's done hardly any E-graph work seems to be completely afraid of, and is always like, no, we're going to do some work to make sure we pull out only these acyclic graphs. But we can actually do cool things with it. So in this E-graph, we've actually got the initial expression represented by the division node here is just 1 over 1 minus a. We're doing a silly little rewrite, so it's equivalent to 1 plus a over 1 minus a. We've introduced a cycle represented by this red part here. And if we keep applying this iteration, we actually end up just at the, if we keep going around the graph in this loop, we just end up at the binomial expansion of 1 over 1 minus a. You know, this is the Taylor expansion, whatever you want to call it. And you can imagine maybe going around this loop. You might, we always talk about truncating terms off our Taylor expressions and things like that in order to get, you know, we want this much precision, maybe we want 3 terms, maybe we want 4 terms, so on and so forth. That could be an interesting space to explore that I haven't really talked about here. But one thing this does allow us to do is if we follow this first red path, this gives us our initial abstraction. But of course, if we then go around the loop again, we might get some new. So here we've got the A1 element, and then we take the intersection of the A1 and the A0, and of course we've added some potentially new information. And so what this actually allowed us to do was then, there are well-known, well-studied iterative methods for arithmetic, one of them being this tri-check method, that basically says if we want to solve AX equal to B, and A and B are just some line, some intervals, we don't know exactly what they are. The elements of these matrices can be variable. How do we actually then find out what our solutions can be? And so there's some update formula for the tri-check method that looks kind of like this. F defined here, because we want to go into it. But as we do this update formula, which is basically equivalent to going around these loops within our graph, we're actually just able to discover this technique. So we can recreate special cases of the tri-check method just by egraph rewriting. And this is cool because, you know, what more can we do with this? What other iterative methods can we discover by egraph rewriting that I guess haven't really been on the radar so far? In terms of results, so we did look at the FP benchmark suite. Basically, if we do exploit these interval arithmetic, we can grow our egraphs up to 84% bigger in some cases just by the fact we can apply conditional rewrites. We learn new conditional rewrites that we can apply, which we wouldn't be able to safely apply without this information. And of course, because intervals are cheap as chips, it only costs 1% runtime overhead. In terms of future work, basically, this is a tangent to my work. I'm interested in optimizing hardware design for egraphs. And you get to a point with optimizing with hardware designs where you realize that the human designers are actually doing something far more clever than just syntactically rewriting. They understand what their intermediate signal values can be. And so this is all building up to, let's integrate this work with our hardware optimization work. But of course, we can look at more powerful abstract domains. So we can talk about relational domains, we can talk about polyhedral domains. We have got a proper paper that's more full than this one, that's gone into FMPad, that's in. But if you want to see it, check out this paper. And my other question is discovering long rewrite sequences is my other big concern at the moment. So if anyone has any grand ideas on that, please tell me. Cool. Any questions?
Any questions for Sam?
So how does extraction work with egraph loops?
Extraction is kind of a, we haven't looked at that problem yet, but you can talk about maybe setting limits as to how many times you're willing to go around a single loop, or you can start thinking about how you actually unroll these loops. I guess it's a really obvious solution, but these things I guess can't be guaranteed. So in all this cyclic work that we had, this only terminates if you actually satisfy the descending chain condition. So my code will just continue to spool. If you put in stupid code, but it's not going to give you a descending chain, so it's A1 less than A1 intersect A0 is less than A0, and this continues to go down without actually terminating, but it will just continue to run. So it's kind of a tricky area.
This is super cool work. Are there other abstract domains that you have tried, or are there any that you're itching to try aside from intervals?
So the cool thing about having the egraph, I guess, is that you talk about sort of one of the most common ones, I think it's called the polyhedral domain, where you start looking at things like A plus B is less than some number, for example. But you kind of always have these intermediate signals, your A minus B in the egraph already. So I guess you can maybe start exploiting how can we get some relational domains. So relational domains is the obvious thing, because intervals suffer from losing any correlation. So that's the main target.
So I'm not sure I
quite understood everything, so this might be a naive question. But it sounded like it was mostly forward abstract interpretation. Have you looked at extracting sort of backwards information where you discover an assertion somewhere down the line and then that has implications, find elsewhere in the graph?
Yeah, I would love to do it. I would love to be able to do it. I don't know what the good techniques are for going in the opposite direction. So going up is easy.
Okay.
Going back down and pushing information down back through the graph, then you're like starting to solve. If I know A plus B is less than 10, what does that tell me about A, for example? Is a less easy question to solve. Sorry, not very satisfying.
Alrighty, let's thank the speaker again. Alright, up next we have our final virtual talk. Alright, so anytime we are ready for you, you step up on the mark.
Yeah, I mean, the predication is music. I was the other side. Look at how
Anytime you want to try saying something?
Yeah, can you hear me?
Yeah, we can hear you and we can see your screen, so take it away whenever you're ready.
Great, thanks. So, hi everyone. My name is David Thomas, and I'm going to present my ongoing work in chapter study and develop calendar graphs. And what we're doing here, trying to do, is support multiple equivalent installations. Each equivalent installation gets a calendar, so it's nice to present it as a finite, which resource sharing, so everything will be efficient. So I'll show you why we're doing this, and then I'll show you exactly what we're doing. So a bit about the motivation. Let's assume we want to do a situation like we usually want to do. On 2/3 the maximum of x and y minus the minimum of x and y. And the absolute value of x minus y, put them both together. Now, you can think about it, you know that the maximum minus the minimum is actually equal to the absolute value. And if we will try to do a situation on this, we will use common sense equalities as definition of the function. So if x is less than y, maximum x y, y is the same for minimum, definition of minimum. And the equal situation won't get us very far because we don't know anything about x and y. So if we don't know if x is less than or greater than y, we won't be able to conclude a lot of interesting things, might affect it. So what can we do? We can do the following thing. Assume x is smaller than y. And once we assume this, and for this slide I'm only focusing on the max minus min, so it is smaller. The other assumption to our graph. And then we can conclude. We can conclude that the minimum of x y is x and the maximum is y. But this changes the graph, and we can take our assumption back, and we would work with the later one to assume that x is greater than or equal to 5. So what we would usually do is we would usually clone a graph before we try to change to add assumptions. But this is very inefficient for the memory. We can run out of memory very quickly once we try to add our assumptions. So what we are trying to achieve is a non-destructive and memory efficient way to have assumptions like x is smaller than 1. And in a non-destructive way, I can have many assumptions. And memory efficient means I won't run out of memory while I'm adding many assumptions. And what this will give us is a bit through case fitting when we are in searching. For the example I showed. That reasoning, and here I mean that if we have locked conditional rewrites, then we can add the assumption on the condition that will unblock our rewrite. And we will be able to apply partial functions, which is very similar to case fitting, or practical reasoning in this format, but just for the cases that are relevant for the partial function. And actually, the even bigger thing I like to look at is having a quality situation with assumption situation. So I have many assumptions going in quality situation to get more quality flow. The thing is, we can't really have assumption situation because a lot of the time we have a recursive structure of this sum pass. And once you have a recursive structure, you can always add assumptions that the structure is bigger and bigger. So you can have different assumptions. But still, we want to achieve as many as we can to get as many conclusions as we can. And how will this look? So we'll go back to the full study. And we'll add a blue equivalence relation on top of the no equivalence relation. And we can show the conclusions in the blue rectangles of what happens if we assume that x is smaller than 1. And same as I showed before, minimum is the x and maximum is y, and the absolute of x minus y will be equal to the maximum minus the minimum. And then we can add another assumption, a different assumption, at the same time, that is that x is greater or equal than y. And then we'll get that the maximum is x, the minimum is y. But again, the maximum minus the minimum is equal to the absolute value of x minus y. And if we did the work, we can conclude that even in the original equivalence relation, these two classes should union. So this is the motivation of how do we actually do it. So our main observation here is that we do not need a clone. It is enough to have additional equivalence relations in the same PLDI. Meaning I have more union finds. I only need more union finds. Not any equivalence relation. Just the cosine equivalence relation. Now, what do I mean when I say cosine equivalence relation? I mean it's an equivalence relation with more unions, meaning more equalities, less equivalence classes. So we're looking at union phi now. And we have the equivalence class represented by 2, and the equivalence class represented by 3, and the equivalence class represented by 1. And I can add another equivalence relation, another union phi, that tells me that 3 is union 2. So the representative of 3 is 1 in the blue equivalence relation. It's a cosine, it has less equivalence classes. Okay, so if we have additional colored union finds, we want to actually show how do we implement the different operations of the eagle. So the most easy operations to implement is the find operation and the union operation, because we can just go to the relevant union find and apply the find union functions. So in this example, I added a color union. And the same color union is just union on the relevant union find. In the red relation between 3 and 2. And if I will try to find what's the representative of 4, I will get that the representative of 4 in the red union find is 2. Of course, if I will want to try to find the representative of 5 and I didn't change anything between 3 and 5 and 1, then I will just fall back to the original equivalence relation and get that the result is 1. That's the original relation, that's like the ground truth. And the relation that I have that are constant, and I added some assumptions to it. But what about other operations? How do I do it without adding more nodes for each relation? So actually, it's not that, it just works, because when you want to add a node to the graph, you just add the node to the graph. It will be shared between all the equivalence relations. When you're trying to do the rebuild, to do content closure, then we can do the same algorithm, but when we get doing the content closure for the current relation, we just need to build the hash funds ahead of time. We don't call the hash funds for each relation. And so we don't really need to do it ahead of time. We need to do it when we're going to do this content closure. But then you can continue because you can access all the nodes and continue the algorithm as usual, sort of. And when we are imaging, we just jump between equal classes during matching. So if I have unions in the blue, if I have the blue relation, I have two classes in original relation, black relation, called original black relation, that are equal in the blue relation. So doing imaging, we will have to go through both of them. The downside of this, it's easy to jump between them, but the downside is that I might find duplicate results that I will need to filter later. So I have multiple matches, I have the same match, and I will get it a few times. And so this might seem a bit inefficient, but here comes another observation from our experience, and that is usually the amount of colored unions we have, the amount of unions on top of the black relation we have is a lot smaller than the amount of classes. And by choosing to look at it like this, we design the implementation to be a little bit more efficient. And in doing the rebuild, doing our content closure, we first put the black content closure. And a lot of all of the conclusions in the black relation are true for the colored ones, because they are only cosine of the black. So we first apply all the conclusions from the black content closure, then do the extra steps for the colored. And if we assume we won't have a lot of unions, and then it will not take a lot of time. And doing imaging, it actually gives us exactly the solution for what we saw before, because we won't have a lot of unions. And sometimes it might not be. For example, maybe your assumption is 2 is equal to false. This will cause a cascade of unions and it can be very expensive. But you want to find these cases ahead of time and choose whether you want to be more memory efficient and use compute. And that's it. Or you can just program to plug in data and still get good results on this specific case. You can still add many assumptions to your data and do all of these operations at once. Okay, do I have more time?
You have a couple minutes. Do you want to move to Q&A or do you have more slides?
It depends. Maybe it's better to have. I have more slides I can show, but if you have questions, maybe better to answer them.
Yeah, I think we should maybe move to Q&A and give it time. So let's thank the speaker. All right, any questions for us about PLDI graphs, multiple E graphs? There are multiple equivalence relations, I guess.
Presumably in some situations where I have like nested abduction, so we introduce one condition and then we have another condition. Is there support for a hierarchy of colors, or do we have to just consider each combination of conditions as separate colors?
So the question is, does this technique support the hierarchy of colors when you have, say, nested conditions, nested abduction, or do you have to basically flatten it into all combinations?
So currently we are flattening it for combinations, but we do want to support the hierarchy. I'm not sure if you will come to some kind of a problem when we're doing this, but I think it should be possible to have it and that's our goal eventually.
Does the implementation of this exist? Because this was really interesting. I mean, maybe one of the most interesting talks of the day for me. This is really a problem that I really wanted to have a solution.
So, Phil asks, this is super cool. It's the coolest thing I've ever seen in my entire life.
Yeah.
Is there code? Where can I click on it?
Yeah, there is code. We are still working on it, so it's not 100% working. Depends on the case. It's actually not that slow. It's a very effective, a normal flow. You can go to my GitHub. I didn't publish it, and if you can find them later, send it to the postdoc.
All right, sounds good. Let's thank the speaker one more time. This is a great talk, Jason.
Thank you.
We're good to go. All right, and this is the last talk of the workshop. Jordan's going to tell us about how to unify everything using. So take it away whenever you're ready. Make sure to unmute yourself on the other.
You need to stand on the podium and gather as well.
A little more circle.
Yeah. Yeah.
All right. So we originally had this very complicated title. My name is Jordan. I'm presenting on behalf of my lab mate Jake and our advisor, Dr. McClure. But I have to thank Sam because Sam renamed my talk during his talk. So I renamed my talk haphazardly applying rubbish rewrite rules because that's actually exactly what we're doing. And I'm here to tell you about all the shenanigans that happens and why in some cases it might actually be cool. But this is actually a very succinct and apt description of what we're doing. So I'm not going to spend any time on the background. You're all here because you already like e-graphs and equality saturation and you know all the cool things it can do. And I'm here to tell you why I'm going to break the equality part of equality saturation and see what happens. So I have had an interest in auto-grading systems and trying to understand how to improve code and how to get feedback and these kinds of things. So I always sort of had this in the back of my head. And when I saw this eGraph work, I thought, wow, this is really cool. Maybe I can do something with this. And so I was kind of thinking about examples like this where it takes 2 seconds to look at this code. It's very straightforward. There's no tricks. There's no anything. It's not equivalent. Semantics preserving rules and eGraphs will never fix this. And so I kind of asked myself, is there anything I could do, though, to try to improve this code? Is there any feedback I can give? Is there any, again, semantics preserving rules are not going to terminate. There's nothing I should expect. So what could I do instead? Is there anything I can return? Is there any feedback? Is there anything I can do? So the motivation for this was to try to extend equality saturation in some way by using what I am kindly calling non-semantics preserving rewrites and basically unleashing the can of worms that you know that will entail by, again, politely calling it expanding the space of rewrites to, I hope, enable repairs that weren't in scope before. And I have this intuition that perhaps I can enable new optimizations that might have been out of scope before. And I'll talk about that a little bit more in a second, while still trying to respect this motivation of giving guarantees of correctness. So in the optimization context, traditionally and I mean sensibly, you must have your optimizations implicit in the rewrite rules. I mean, you may have unique combinations. I'm aware this paper Ruler came out of, I think, your lab recently that's improving this to help it so that users don't necessarily have to exclusively provide and debug rules. But again, there's still this notion that the optimizations are implicit in the rewrite rules. And so for the work I'm talking about today, I just want to be clear up front. I'm requiring a concrete coding specification that's going to be important. I want to relax that later, but right now, like, I am going to use a concrete spec, and again, I'll show you an example here in a second. But then what's cool about this is maybe now program repair is in the wheelhouse of this by altering the semantics of the input, because in the program repair space,
you know there must need to be some non-zero number of what I'm calling non-semantics preserving rewrites, or else program repair can't possibly work. So one way to think about this, and the very first example I pitched to people is will you buy that if I'm trying to rewrite x plus 1 to x plus 2, that a way I could do this is to lie to the e-graph in union 1 and 2 into the same e-class and say, pretend these are equal, and it says, okay, cool, those are equivalent. And I say, okay, cool, that's a repair. And I agree a lot of consequences immediately cascade from that, but I think there is something interesting there. So I'm proposing a very, very naive search to just take sort of atomic expressions from both. But the goal is to use the new explanation mechanism that A has to sort of lie to the e-graph and then see if it will give me something cool at the end. And as kind of a spoiler, I have preliminary results that it kind of does. So let's revisit our example here. What the tool is essentially going to give back to me is that, okay, if you set I equal to 0 in the input program and I equal to 1 in the specification program, you can look at the rest of the program and say there's no way that that can work. And so through the search example I'm going to show on the next slide, basically what's going to happen is I'm going to use a non-semantics preserving rule to union 0 and 1 into the same e-class. And similarly on the next line, on the left-hand sides, A and D are not equivalent, so they're going to have to be unioned. But A can already handle the right-hand side because I times 2 and I left shift 1 are equivalent. And it basically goes through all this together. Nothing's needed on the last line. I need to union A. Line 3 is a little bit tricky. This is my naive pitch at discovering an optimization. I want to be very clear that if you have commutativity of addition, this isn't needed. But I use this as a starting point to say, unioning A and B actually allows you to stumble your way through something that approximates commutativity of addition, because if A thinks A and B are equal, then it will actually subtract these two terms, and then it will rewrite the A to a B to match the specification that's left. And so A will actually stumble its way through and repair this, and give you a chain of rewrites that says, yes, under these ridiculous assumptions, I can turn the input into the specification. And my big one-sentence takeaway pitch from this is, that's kind of cool, and I'd like to use that for feedback. And so my first naive approach at doing this, just to talk a little bit about implementation, I called it a graph of e-graphs, because basically what I did is I took the input e-graph and I tried just sort of unioning things one at a time and seeing if any of those could fix it. And it literally was, think of a breadth-first search, try doing one union at a time, and ask for an explanation. If no explanation exists, that must have not fixed it. So I try all the single unions, I try all the pairs, I try all the triples. Clearly performance problems, but again, still, just a starting point. So this does give you some notion of minimality if you can make the thing terminate, because you assume if you found a 2 union fix, that meant none of the ones existed because you tried them all. And it actually produces fairly small, fairly readable outputs that I think a user could learn something from. And I think this lends itself nicely to feedback. You already know what the cons are. This is going to grow exponentially. It's not going to scale. We're well aware of that. I'm not trying to lie to you and pretend that this solves complexity problems. You know that it doesn't. But I'll show you a plot in a second that shows we might be able to approach some reasonable problems. So I took this example out of a paper called Search, Align, and Repair. It's from Microsoft Research. Basically, they took some coding examples from a big, massive online course that they have. And the code on the left is the student code. The code on the right is instructor code that they sort of paired it up to. You're basically trying to write a chessboard alternating X's and O's. The student accidentally, so this first box is just showing a variable renaming. That's not an error, but we're going to have to understand that mapping. The student did make an error here. It's supposed to be I plus J mod 2 instead of just J mod 2, so we're going to have to fix that. And they accidentally put a 0 instead of an O. And the moral of the story is, through shenanigans, I trick Egg into rewriting J into, say, J plus 0, and then rewriting 0 into I, and then maybe switching some things around. And again, I sort of trick Egg into doing this for me, and through search, get it to fix this. Is that the best way to do it? Maybe not. But I think it's kind of cool that it terminated in a reasonable amount of time. And by reasonable, I mean under a minute. So this wasn't like a second because I had to do some variable renaming that I would like to be agnostic to in the future. But including the 3 fixes of basically understanding that the variable chess and the variable query are the same thing, figuring out that I need to go from j to I plus j and rewriting this O to 0 took me about a minute to naively search through a bunch of stuff. I have another benchmark, it's called Quick's Bugs. I pulled one of theirs out. It only needs one fix, it runs really fast, it's not crazy interesting, but I just grabbed those to show I'm not trying to build only contrived examples that will work with this. I proved some memory stuff by doing some hacky tricks. It's not really the main moral of the story here though. The point is though, this is a log scale on the y-axis, so your intuition that this is growing exponentially is correct, both in time and the amount of steps my tool needs to use. So then, and this is probably going to make some people even more sad, I decided to see if I could break this even further, and the answer is you can. And so I basically was just like, well, what if I've already lied to A. Let's lie to A more and just like union a whole bunch of things. And so I thought this was just going to be this like terrible comparison that I ran and then forgot about, until it like kind of worked. So basically what I did is I just started unioning things like crazy. And then I was like, hey, A, can you explain to me how to take this nonsense over here into a final solution? And it runs really, really fast because it uses some of the strengths of A. And so heavily caveated, if I have a specification to rewrite to, I can produce a chain of rewrites to get there. So if you don't have a spec, then you throw everything away that I just said. But it runs really fast. I never got it to take more than like 10 milliseconds because it's using the strengths of the rewriting engine. It's really simple to implement. Again, mileage may vary on the input, but it gives really complicated and really bad outputs. I'll show you a plot in a second. The insights are not profound, but it was kind of an interesting balance. So I've calculated my own cost metric. It's basically just a multiplication of two things, but nothing on this plot needed more than 6 fixes. Most of them needed like 2 or 3, and some of these are using 500 rewrite rules to fix. So again, this is not some end-all be-all magical fix. Egg is running really, really fast, but it's just doing a lot of crazy stuff a human would never do. But again, I think it's cool that it terminates quickly and that it gives me something back. And maybe that there's some post-processing that I could do or something to bring that back down to something reasonable. But the moral of the story is, what I'm trying to propose in this talk then is that maybe there's something, like there's a phrase, shenanigans beget shenanigans, which is basically title 3 to this whole talk, but like maybe somewhere in the midst of the shenanigans is something reasonable. And so what we'd like to do is try to find some balance between these two approaches, because they're both sort of nonsensical in different ways, but maybe there's something in the middle. Maybe that's an extension to the eGraph, something like sharing expressions. I kind of think of it sometimes as like collapsing down my graph of eGraphs, but basically the idea being, Egg is really good at the semantics preserving rules, and I can let it saturate or I can let it run and see what it can produce, but these non-semantics preserving rules probably need to be handled in some different way. I have a sort of really simple example to kind of visualize that. Maybe I have some expression like A equals B plus 1, and I'm going to try to just change that into A equals B plus 2. So again, this notion of needing some sort of non-semantics preserving rule. And if I just had simple IDs, maybe I could think of like an in-order traversal type thing. What we're really trying to do is union 1 and 2 into the same E-class. So I have drawn them. I was trying to draw like 2 planes, which is to say that the input was A equals B plus 1, but what I'm really trying to do is union 1 and 2, and through some sharing, not have to store the entire new eGraph and say, oh, this prefix is the same, but really what I changed is back here, and I'm sort of tentatively putting those together until I can either prove or, in reference to the CAD paper, undo that rewrite, an inverse transformation, if you will, or something. In the case of having a specification, though, maybe I can just prove at the end that the two are equivalent and I'm okay. But hopefully there's maybe some middle ground here that will allow memory to be somewhat efficient. Again, I'm under no disillusion that I'm magically going to dodge all complexity problems and all problems in the space. The moral of the story at the end here being that, yes, there's a lot of limitations, so I want to be very clear. We're requiring a strict specification. That's probably unrealistic for certain use cases. This probably is not going to scale super well to really large programs, although I do think that's something cool about Egg. The fact that the data structure does a lot of sharing naturally means that you can keep scaling the program as long as you're sort of reusing the same variables. And if you only need a handful of non-semantics preserving fixes, this actually will scale extremely well. It's when you start getting a lot of unique expressions and stuff that it's going to take it pretty fast. Again, at some point you have to ask, if you can rewrite anything to anything and there are no rules, what does anything mean? So you have to have some sort of some realistic bound. But again, there's this caveat on if quality saturation is founded on equality. What are we really doing here? But I hope I've convinced you it's maybe worth exploring. So in our future work, we're thinking about these scalability issues because that paper I referenced indicates that approximately 3 repairs does a lot in certain domains, namely computer science education. I don't think that that's true in any and all domains, but 3 repairs is in our wheelhouse. So I think that's exciting. I think being able to take the chain of rewrites and try to extract feedback is also exciting because I think there's a natural mapping between the two. I also think there's exciting opportunities to use the different kinds of rewrite rules differently. For example, if I rewrite x times 2 to x left shift 1, that might still be feedback I want to give a student. And then either through a TA discussion or through discovery or whatever, understand why a bit shift is cheaper than a multiplication and why the tool suggested that maybe we should try one over the other. And then of course the key idea being that the non-semantics preserving rules, the need to use them indicates a repair. So basically there's still open questions. Can I actually discover cool novel optimizations? Still investigating that. Can I relax my specification? Not sure. But the key takeaways on my last slide here, just I think there's some potential here. I think it's cool that we can use semantics and non-semantics preserving rules. We can sort of open up the floodgates a little bit, let it run for some time and see what we come back with. Maybe we got a cool optimization that wasn't in the original rules. Maybe we got a repair if we have a spec to work towards. And I think there's, again, a strong ability to maybe create feedback from these. CS education is a really cool domain because it's not unreasonable to ask for a specification, whereas elsewhere it might be. And I at least have a hacked together prototype that shows some early success on this. So that's my last slide. I will stop there if there are any questions. Sure.
Nice talk. So, so your motivation was from computer science tutoring, and then you marked that future work. But could you please elaborate? How would you see what kind of feedback a student can get out of your correctness breaking transformations? How exactly is it helpful to learn how to write better code?
Yeah. So the question is, what type of feedback could I provide to a student? Yeah. So in its current form, it's not super decipherable. What I would like to do is say essentially a post-processing step, and I envision one of 2 things. One is you present very specific rewrites of sub-expressions where you can go down a hierarchy, maybe highlighting a problematic line, problematic sub-expression, or a literal rewrite this expression to this expression, just to give different levels of hints. But the second part to that is you might be trying to present it in such a way that a student understands, oh, I had it off by 1 error, and I see the sub-expression happened, and then they reason themselves to why that was the problem. But also in the context of both a semantics preserving or non-semantics preserving fix, I'd also love to see if it could be a conversation starter for, say, office hours. Because there are many instances where I think, I don't know, has anyone ever TA'd a class where someone brought you like 50 lines of code and said it's broken and thought you could just look at it and know where the bug was, and like they're surprised when you can't? If it highlighted a sub-expression, they're like, it says that I need to change this 1 to a 2 or this A to B, I don't know why. I think that localization is actually really important, and it can help focus efforts of, say, TAs or instructors down to parsing out a whole bunch of stuff that's not really the problem. Because Egg will not complain about rewriting 10 of the 12 lines if it believes they're equivalent under semantics preserving rules. It will say, no, these are equivalent, don't worry about that. But this line down here, I can't fix that. And maybe it's a conversation starter. So I can see a lot of different ways.
But you assume that the reference solution exists, right? So you need to have the target of the rewrites in order to...
Right, and I think in computer science education, that's perfectly reasonable to ask an instructor, hey, I need to know what you think the answer to your code is. That is obviously going to be challenging in other domains. I thought about, for example, maybe like different Git diffs, if I could maybe try to do some chains of rewrites between different Git diffs and understand something about what changed, but we'll see. Did you have a question as well? Sorry.
Oh yeah, I was going to say, really random, it completely destroys your input constraint size, but like in this, the whole repair problem is a big thing in like hardware design and netlists that come out of it, and we want to make these small changes that fix our netlists. Do you have any feel for what you do if you just threw in a rule that was like, turn an AND gate into an OR gate?
Yeah, so to be fair, that's like exactly what we're doing. Is, again, these like ridiculous statements that in no universe is 1 equal to 2, but like maybe if I make that assumption, can something interesting happen from it? So I think the hardware analogy, just turning an AND gate into an OR gate, is exactly that. And if we, but like you have to have something to sort of work towards, right? So I either need to know the answer in advance, which in some domains is a perfectly unrealistic assumption, or you need to have some way to vet, like, did something useful happen, right, at a high level. So did changing that AND gate to an OR gate do something useful? So even if you had a large circuit, if only a few of those changes were needed and you had some sense of knowing progress, I think that could actually be very interesting. But in certain domains, asking people to already know the answer is ridiculous. And in certain domains, it's perfectly reasonable, and that's also part of the space we're kind of parsing through. Yeah. I thought I saw another hand.
Well, I think we are